Welcome to Volcanoes and Volcanic Ash. This is the first of a two-part series. This is part one, put together by myself, Jeff Braun. I work here at Terra, associated with the ShyMet and Visit programs. I put this together with Jeff Oshinsky, who's the Deputy Chief of the ESSD, the Environmental and Science Services Division, up in the Alaska region. I also had a great deal of help from Bernie Connell, also works here at Terra, associated with the ShyMet program. Christine Nelson, who's the MIC at the Anchorage Center Weather Service Unit, or CWSU, up there in Alaska. And also Tony Hall, who is the MIC of the Alaskan Aviation Weather Unit and the VAC, and we'll talk more about those later. And we had a lot of additional information provided by a multitude of others, so thank you very much to everybody who helped in this. Perhaps the most significant question of this entire session is why, and that's a great question. Why are we doing this? And it's answered quite simply by Vice Admiral Donald Edgen back in 1991, a true aviation legend, who stated that ash clouds are not an everyday issue, and they do not provide frequent hazard, but if encountered, volcanic ash can spoil your entire day. And that pretty much sums up any catastrophic hazard type event which volcanoes and volcanic ash definitely fall into. A most recent example, of course, that we're all familiar with is the Iceland volcano, which is called Eyjafjallajökull, and I will be referencing it most of the time as the Iceland volcano, or in science circles it's sometimes known as E15, just to avoid trying to spit out Eyjafjallajökull too many times. It's pretty hard to do. That volcano in Iceland, the main eruption period during mid-April from the 14th through the 24th, 10-day period, caused, just in that 10-day period, $2 billion loss in revenue. At one time, 27 major airports were closed. Over 90,000 flights were canceled over a 2-week period. The mobility of people everywhere and the ability to transport food, medicine, machinery, and everything else that you can imagine in and out of the European airports and into the countries was halted for a great period of time or significantly slowed down. The global impact overall was tremendous. Why we're worried about that here in the United States, that Iceland volcano did affect us here in the United States, trying to get goods and people in and out of Europe and back here to the United States, but also just referencing a recent volcano, or relatively recent in geologic terms, the main St Helens eruption back in 1980, you can see the area of fallout stretches all the way across the Rocky Mountain west here, and that has significant impact on aviation purposes and a lot of other transportation going in and out of the region. And if this were to occur today with the heavier aviation traffic, it could impede a lot of our commerce for days and days, weeks, or maybe even months on end. You can see up here close, of course, it's going to be a physical health hazard, a physical hazard to the forest, to people anywhere even close, but the reaches are much farther out, when you look at it overall. And we'll be looking at how some volcanoes could potentially impact the entire United States later on. Here's a quick look at some of the other historic volcanic eruptions in our area and their far-reaching effects. You can see here's Mount St. Helens here in the middle. That was relatively small, and again, of course, the ash did spread out a lot further than just this tight area here up in Washington, Oregon, and Idaho. But we also have the Crater Lake eruption that's shown here, the Long Valley Caldera eruption, which goes all the way out across most of the southwest. And then we have the Yellowstone caldera, which actually reached all the way out here into the Midwest. So you can see a lot of these areas here are extremely, if any of these go at any time, and the thing with geologic hazards like volcanic eruptions, you just never know when it's going to happen. Here's a look at our recent active or relatively active or potentially active volcanoes in the western United States, and we've got a good deal of them, and we've only had one erupt relatively recently, and that was Mount St. Helens, but it's only a matter of time before we start lighting up some of these other ones around, and the main idea here is to remain aware and to remain frosty over a situation like this and kind of know what you're getting into if or when one of these happens. And now for a few examples of some hypothetical eruptions in the United States, the western United States, that would show the potential impact of volcanic eruptions. These are provided by the high-split 48-hour trajectory forecast model. And we're starting first up with Mount Rainier here in southern Washington. And you can see over a 48-hour period what kind of impact it would have. It would effectively cut off all of Oregon in this case, a good deal of access to southern Washington and some parts of northern California. And of course, this is just a model forecast that may even have farther-reaching effects than this. We move a little bit further south down to Mount Lassen, California, which did erupt earlier in the 1900s. On this particular day, if it had erupted, it would effectively cut off most of the north-south travel for a period of time over the western United States from, say, Arizona, on up to points north in Oregon, Washington, Canada, etc. Or you'd have to severely reroute air traffic around this, costing a lot more money, of course, and fuel costs. So you want to keep those kind of things in mind. We move over to Mount Shasta, a little bit further north on the same day. Similar type situation, cutting off most of access to Nevada, or the important points in Nevada, except for Las Vegas, but also cutting off north-south travel or rerouting it in the area. Then we move on to the supervolcanoes. This is the Long Valley caldera in eastern parts of California, and you can see a 48-hour eruption in this case would effectively cut off almost all or most of the United States for a period of time, depending on the concentration of the ash flowing, limiting access from the southern parts of United States to points in Canada or Alaska, because you can see the drift, how far it goes. So that's something you want to keep in mind too. And then last but not least, we showed the Yellowstone caldera, another supervolcano. If it had erupted on that day in July 20th, it would effectively cuts off all of Montana and then also a good part of access to Canada up here. So even though these are all hypothetical eruptions, these also help to answer the reason why we need to keep these kind of things in the back of our mind, why they're important, and the kind of impact that we're talking about. And this is just over an eruption that we follow the ash for a 48-hour period. If we have continual eruptions over a longer period of time, you can see how the impact would be huge or great or very significant here in the United States. The objectives for Part 1 of Volcanoes and Volcanic Ash are pretty straightforward. We're going to be discussing, of course, some of the geology and looking at the volcano types. Then we'll be looking at hazards on the ground and in the air, looking at a little bit of the health hazards. And then, of course, we're going to wander into aviation hazards and the issues associated with those, because those are a huge impact in the volcanic ash kind of situation. We'll be following that up with ash and aerosol detection of various sorts, observation platforms. We'll be looking at satellite radar and other types of information that we can get concerning volcanic eruptions. And then we'll be ending Part 1 with a look at the modeling, just like the high-split model we looked at previously. We'll be looking at a few other models and see how the models handle plume dispersion and how important that is to the volcanic ash forecasting process. First up is a look at the geological portion of this session, and that's volcanoes themselves, as they are the main hazard and the main problem in this case. We'll be looking at three main types of volcanoes. We'll be then dividing that into a few different eruption types within those volcanoes, and we'll even be looking at a few of the eruption mechanisms within those eruption types. Hopefully this will give us an idea of the type of impact provided by different kinds of volcanoes and eruption mechanisms. First, we'll take a look at a cinder cone example. They're the simplest type of volcano. This is a photo of Parícutin, which is west of Mexico City, and it first erupted in 1943 and grew right out of a farmer's cornfield. It is built from particles and blobs of congealed lava ejected from a single vent, and as the gas-charged lava is blown violently into the air, it breaks into smaller fragments that solidify and fall as cinders around the vent to form a circular or oval cone. Most cinder cones have a bowl-shaped crater at the summit and rarely rise more than a few thousand feet above the surroundings. Cinder cones are very numerous out here in western North America, as well as throughout other volcanic terrains around the world. They have an impact physically and as a hazard, of course, immediately in the area that they grow out of, but are generally not considered as volatile or dangerous as some of the other volcano examples that we're going to show here in a minute. Now, here is a dangerous type of volcano. Of course, this is a photo of Mount St Helens during the eruption on May 18, 1980, and it is a composite or stratovolcano. These are typically steep-sided, symmetrical cones of large dimension built in alternating layers of lava flows, volcanic ash, cinders, blocks, bombs, and all this conglomerate may be put together and rise as much as 8,000 feet above the bases. Some of the most conspicuous and beautiful mountains in the world are composites, including Mount St. Helens here, of course, Mount Fuji in Japan, Mount Cotopaxi in Ecuador, Mount Shasta in California, and Mount Hood in Oregon. These are dangerous. They put a lot of debris into the air and have a huge impact, not only in the local area surrounding the volcano, but, of course, the far-reaching effects of the volcanic ash itself going into the atmosphere. The third type of volcano we'll discuss is the shield volcano. Shown here is Mauna Loa in Hawaii, the largest volcano on Earth in terms of volume, which covers approximately 18,000 cubic miles of material and is one of 5 volcanoes that form the island of Hawaii and has been erupting for about 700,000 years. Shield volcanoes are built most entirely of fluid lava flows, where you get flow after flow after flow pouring out in all directions from a central vent or group of vents, building a broad, gently sloping cone with a profile much like a warrior's shield. These type of volcanoes generally fall in the middle between cinder cones and composite volcanoes. As far as hazards go, they do put a lot of material in the air at times, but aren't quite as explosive as composite volcanoes. Moving on to volcanic eruption types, there are 2 broad categories. The first is effusive eruptions, and these are the ones that are not so dangerous and are generally dominated by passive emission of lava. These are basaltic eruptions and are the type that you can walk up to and observe on your vacation. Good examples, of course, are in Hawaii at Kilauea and Mauna Loa both, generally forming rows of fountains and lava flows made of that basaltic magma. The dangerous one, and the one that we talk about or refer to most often in this session, are explosive eruptions and are dominated by the eruption of pyroclastic material that eject large quantities of tephra into the atmosphere. Some of this ash can be shot as high as the top of the troposphere or lower stratosphere. Mount St. Helens in Washington and Okmok are very good examples of this type of eruption. Here are about 3 of the more common eruption mechanisms associated with some of the volcanoes and eruption types we've been talking about. First up is a phreatic eruption, and it's caused when water and heated volcanic rocks interact with each other and you get violent explosions from this. In this case, magma is not involved. Mount St. Helens is a good example of this kind of eruption mechanism. Phreatomagmatic eruptions are defined by interaction between water and magma. You also get the explosive thermal contraction, and you get a lot of explosions caused as the magmatic particles cool very rapidly with the contact of water. In this case, Mount Okmok in Alaska is a good example of that type of eruption mechanism. And then you finally have magmatic eruptions caused by rapid decompression of the magma, therefore releasing dissolved gases very quickly and sometimes explosively, causing fountains and flowing associated with shield volcanoes. And, of course, we already saw a good example of this with Mauna Loa. Of course, many times volcanoes will use more than one eruption mechanism. or even more than one eruption type. A good example of that is Okmok, which is a composite volcano, and usually falls into the explosive type of eruption, but the mechanisms may vary in this particular situation. Here are two good examples that happen at the Okmok volcano. The top one is a phreomagmatic eruption, which we talked about before, and it's the interaction between water and magma that releases both magmatic gases and steam caused by the contact of magma with the groundwater, or in this case the ocean water. And you get the extreme temperature of the magma causes instantaneous evaporation of the steam, resulting in the explosion of water, ash, rock, and volcanic bombs. In this bottom type, we have a strombolian eruption, which is also the same thing as a magmatic eruption, and it's characterized by huge clouds of molten lava bursting from the crater to form arcs through the sky and fountains. Sometimes the explosions are driven by the burst of gas that rises faster than the surrounding magma. So there you have two different mechanisms within one volcano type, but producing a couple of different types of reactions, but both are very dangerous. Now that we've finished the mini geology lesson, we'll get into some of the hazards themselves. Volcanic eruptions and ash production can cause great hardship to those local and regional communities which lay close or under the direct effects of a volcano, or even far away as far as volcanic ash goes. These effects range wildly from property damage to health hazards. Volcanic eruptions with plumes of drifting ash clouds not only cause substantial delays in flight operations around the world, but can also produce significant damage to both aircraft and the equipment. This diagram shows many of the inherent dangers associated with volcanoes. Some of the more classic ones are pyroclastic flow, landslides, ash clouds, of course. We'll talk about much more of those later. Acid rain falling from the interaction of the atmospheric moisture with ash and gases in the atmosphere. Tephra, which is just another word for fragments of volcanic rock that's put up, usually more coarse than ash, and lahars and lava flows, of course. And we'll look a little closer at some of these in just a minute. First up with the hazards, pyroclastic flow. Here's a photo of the Mauna volcano in the Philippines during eruption on September 23, 1984, showing the pyroclastic flow area down the side of the mountain. These are high-density mixtures of hot, dry rock fragments and hot gases together that move away from the central vent at very high speeds. During the explosive volcanic eruptions, they produce gravity flows or currents where you get the mixture of hot gas and rock together, known as tephra, and it's really sort of a plasma which moves down and travels away from the central part of the volcano at speeds up to 450 miles an hour. The gas can reach temperatures of around 1,000 degrees centigrade, and these flows normally hug the ground as they accelerate downhill, spreading laterally if the terrain is appropriately shaped under the force of gravity. It's sort of the rocky analogy of a meteorological combination of sorts, where you have the collapse of the ventilation column within the volcano itself, or here's another look at during the eruption off of St Helens, showing a pyroclastic flow down the side of that mountain also. You get the collapse of the ventilation column, which is the close analogy to the collapse of a thunderstorm producing a downburst. And then, as you get that, because of the collapse of the ventilation column and all that force of gravity, you also get the acceleration downslope after that, which is similar to the gravity acceleration for a katabatic wind, when you get the cold, dense air moving down the side of a mountain. Anyway, their speed depends on the density current, the volcanic rate output, or how strong the eruption is, and the gradient of the slope itself. Obviously, inhaled ash particles from within the hot, dense plasma of the pyroclastic flow almost always result in death from severe burns or asphyxiation. Here are a couple of examples of a lahar, which is a mixture of water, rock fragments, ash, mud, dirt, moving down the side of a mountain under the force of gravity very quickly, showing what kind of damage can be done Obviously, here we see the heights of some of these lahar, or depth of some of the lahars reaching up to 40 or 50 feet above the surface of the ground, and can do a great deal of damage. Or in other cases, they can carry with them these gigantic boulders, and obviously anything in the path of the boulders or the mud or the ash or the water in these cases can be very hazardous and also cause death and a great deal of property damage. Other hazards associated with volcanoes include ash and sulfate aerosols, which can cause significant damage to airframes and engine components. You can get in-flight engine loss, wheel abrasion or crazing of the outside of the aircraft itself, instrument damage to the electronics or the hydraulics. Ash avoidance causes many substantial delays in flight operations, causing great loss in revenue, and also unknown health hazards associated with some of the gases themselves. Volcanic plumes. Over the last 35 years, there have been about 120 documented aircraft encounters with volcanic ash, all of which sustained some sort of damage. Total repair cost for these 120 documented encounters is around $300 million. At least 9 of these encounters resulted in temporary engine failure. 3 of the aircraft lost power to all the engines for a period of time. These engine failures have occurred at distances ranging anywhere from 150 to 600 miles away from the volcano, so you can see you don't have to be right next to the volcano for these things to be significant. And back on the ground, explosive eruptions can destroy vegetation over wide areas by depositing volcanic rocks and ash over wide areas. Mud and debris flows, flash flooding, wildland fires, hot ash flows, all from some eruptions. Irritants to eyes, skin, and respiratory systems of humans and other animals can occur due to both the ash and the gases themselves, sulfates, carbonates, nitrates, and hydrofluorides, causing acid production when mixed with water. And that's not only within the respiratory system or on the skin of human beings. This can be water in the atmosphere or even groundwater systems that can form acid, thus destroying vegetation over wide areas. You can get collapsed roofs due to the heavy ashfall. Damage to mechanical and electrical equipment is obvious, to many things on the ground, and also great impact to ground transportation as you get very slippery surfaces formed, and also in some cases entire roads destroyed that are close to the volcano itself. On December 15, 1989, the crew of the KLM Flight 867 struggled to restart the plane's engines as smoke and strong odor of sulfur filled the aircraft. For 5 long minutes, the 747 jetliner, bound for Anchorage, Alaska, fell silent as it drifted towards the Talkeetna Mountains in Alaska. All 4 engines had flamed out when the aircraft inadvertently entered a cloud of ash blown from the erupting Redoubt volcano 150 miles away, shown here in the photo. The volcano had begun erupting 10 hours earlier on that morning of December 15, 1989, and only after the crippled jet had dropped from an altitude of 27,900 feet to 13,300 feet were they able to restart the engines and land the plane safely in Anchorage. Such dangerous and costly encounters between aircraft and volcanic ash can happen because ash clouds are difficult to distinguish from ordinary clouds and are visually sometimes indistinguishable and also hard to find on radar at times. Also, the ash clouds can drift great distances from their source, and it's a very hard process to forecast the drift of these clouds. When we are looking at the synopsis of what happened on the KLM Flight 867, all 4 engines had failed within 59 seconds. False cargo compartment fire warnings went off, requiring special attention by the crew and wasting some of the crew's time. Airspeed indicators failed, avionics overheated and started to fail. Engines eventually restarted after nearly 5 minutes, but were at reduced performance, but luckily enough to get them down on the ground. Eventually, the aircraft landed, and there was $80 million in damage to the aircraft itself. Here's also a look at another volcanic ash scene that took place back in World War II. Here in Italy, 88 B-25 aircraft of the United States Air Force were buried in volcanic ash from the eruption of Mount Vesuvius in Italy in March of 1944. So it can happen anytime, anywhere in some instances. And, of course, this was during World War II, so not something that we needed at the time. What is volcanic ash? Well, there are the three mechanisms that we talked about earlier of forming volcanic ash. We had the magmatic, the phreatomagmatic, and the phreatic eruptions. They all release gases under decompression. They cause the ejected materials to explode, either moving up into the air as they expand or on contact with each other or on the ground, and can be torn into many particles of various sizes from clay to sand, which can stay in the air for extended periods. Volcanic ash is essentially volcanic glass, rock, minerals mainly made out of silica for the most part. There are many different other variations too, but they're generally rich in silica, and the size varies from 1,000th of a millimeter up to 2 millimeters, and each of those can stay airborne for various times. Obviously, the smaller the size, the longer in the atmosphere. And it's very hard and rough, abrasive, can ruin windows, can ruin the exterior of aircrafts, can scratch and get into places that it shouldn't be. It's mostly insoluble in water, although some of the oxides with salt will oxidize and actually slowly burn in the presence of water, making it very corrosive in that kind of situation too. Here's a look at the ash actually from Mount St Helens during the eruption back in 1980. In this particular case, the ash cloud during the explosive process actually reached 90,000 feet in less than 30 minutes, well above the tropopause and the stratospheric cap. The ash made its way all the way around the world in about 2 weeks. But in this case, because it was located in a rather remote area, it only messed up and canceled about 1,000 commercial flights during that period of time, compared to the 60,000 flights that were delayed in Europe over a 10-day period with the Iceland volcano. So location, 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 it can mean everything, even with volcanic eruptions. Here's a generalized look at volcanic ash hazards. It's abrasive and dense, can cause damage to machinery, and obviously if you get too much of it on the roof, it can load and cause the buildings to collapse. It's conductive and can mess up electronics and power grids. It's very small, or part of it's very small, and it can infiltrate into many places it shouldn't be, and also is a great respiratory concern because of this factor. The fallout from ash, most ash particles that are greater than 0.5 millimeter fall out near the volcano, within 25 kilometers anyway, within the first hour, which is good. However, the finely grained ash typically falls out much later. It takes 12 to 24 hours and can drift distances of hundreds to thousands of kilometers depending on the atmospheric conditions, making it very hard to forecast at times. The smallest, when you get into the diameters that are much, much less than a millimeter, in the thousandth of a millimeter category, these drifting ash clouds can be hazardous to aviation over huge distances of thousands of kilometers or miles. Volcanic ash as a health hazard is second to none. Here's a photo of Clark Air Force Base in June 1991 after the eruption of Mount Pinatubo in the Philippines, showing collapsed roofs due to heavy ashfall. Long-term exposure to breathable ash particles, generally less than 10 microns, will result in acute symptoms such as nasal irritation, throat irritation, and dry coughing. And for people with pre-existing respiratory problems, severe bronchitis is the result, often with symptoms lasting from weeks to months after the ashfall itself. Also, eye and skin irritation and damage are common side effects of exposure to airborne ash. Here we have a look at what's known as volcanic smog, or VOG. This photo was taken from the NOAA 15 satellite, July 10, 2008, of the Kilauea volcano in Hawaii. Fog is formed when SO2 and other gases emitted by an erupting volcano, in this case Kilauea, mix with oxygen and moisture in the presence of sunlight. Kilauea itself emits an estimated 2,000 tons of fog every single day. Here's a photo, a ground shot of Pyroclastic Flow. We talked about that a little bit earlier. Here's a ground shot showing the ash cloud having moved down the side of the mountain. This is in the Philippines off of Pinatubo Oso, and expanding very quickly and fast down the more gentle slopes as it hits, and it's actually chasing this truck and driver right here, who hopefully will get out of the way. The problem with pyroclastic flow is that any inhaled ash particles from this hot, dense flow will almost always result in death from burns or asphyxiation. And then we follow this up with volcanic ashes, which also can be co-located with ash sometimes, and sometimes they can be off in other areas not located with the ash itself. Here's actually a photo from Mammoth Mountain in California in 1990 showing the results of carbon dioxide poisoning. Dead and dying trees on the south side of the Mammoth Mountain were first noticed back in 1990, and since then about 170 acres of trees have died on all sides of the volcano, especially near Horseshoe Lake. When the soil was surveyed in 1994 for carbon dioxide gas, exceptionally high concentrations were found in and around the soil and the trees in the area. The most abundant volcanic gases are shown here and down here, and they're in descending order of abundance, with water coming in first. Not hazardous, but it's the first gas up. Secondly, followed by high concentrations often of carbon dioxide, and that closely followed by sulfates. The trace gases include hydrogen sulfide, hydrogen gas, carbon monoxide, which is another great poison gas, and then two acids here, which come out in gaseous form and can mix with water in the area and cause them to become highly acidic, and also killing a lot of the vegetation and hurting the animal populations in certain areas. The volcanic gases that pose the greatest potential hazard to people and animals are the sulfates, carbon dioxide, and the hydrofluoric acids. Volcanic ash as hazards to aviation is also second to none. Here's a photo in May 23, 2006 of Mount Cleveland in Alaska erupting, showing the ash column coming out of it. Even though this is rather small at the time, the ash fall and the ash drift would be concerns for an extended period of time of a few days after this. What we're showing here is the generalized areas where you can get damage to aircraft both in the air and on the ground. Obviously, ingestion by the engines, which we mentioned in the KLM flight, is dangerous with loss of performance or complete shutdown. Also, damage to the leading surfaces of aircraft. You can have landing lights and windows being damaged or crazed so that you can't see or use them any longer. Also, significant hazards to aircraft can occur to the windscreens, windows, the external probes that tell pilots that the airspeed, what their airspeed is and the altitude they're at. It can ruin the antenna for communication navigation, and it can almost instantaneously at times, if it's small enough, contaminate onboard electronic equipment, air conditioning, and cooling systems, and even get into the fuel system and the hydraulic systems that will control the landing gear. So you can see how hazardous this is at all stages of flight, whether you're in the air or even if you're on the ground. In this case, we had so much weight on the back end of this. This is again in the Philippines, that it actually brought the back end of the aircraft down to the ground while it was parked. Volcanic ash in aircraft, just what is enough? Well, as it turns out, it doesn't take too much ash to do damage. This photo is from an encounter in February of 2000 on a NASA DC-8 research aircraft that flew through a diffuse volcanic ash cloud produced from Mount Helka volcano. They encountered this in total darkness with no moon at all early in the morning of February 28th, and there were no indications to the crew at the time, but the sensitive onboard equipment and instruments aboard this research aircraft detected the 35-hour-old ash plume. Upon landing, there was no visible damage to the aircraft or the engine's first-aid fan blades, but later close-up inspection, shown here in the photos, revealed clogged turbine cooling air passages. Some of the more recent ideas in just what kind of concentration we're talking about is as little as 2 milligrams per meter cubed, but there's also a question of the time period that you have to fly through one of these type of diffuse clouds. So there's a lot to be answered here, a lot of research to do before we find a definitive answer, and it may differ greatly between the type of engines, even jet engines themselves, as to how much damage can be produced over a certain period of time. By the way, the total cost of refurbishment of this particular aircraft to all four engines was $3.2 million, and something that couldn't even be seen very well. Here's a kind of a close-up view of volcanic ash effects on jet engines. The ingestion of volcanic ash by the engines can cause serious deterioration of engine performance, sometimes stalling, due to the erosion of the moving parts or partial or complete blocking of the nozzles, which we saw in the previous photo. Volcanic ash contains particles whose melting point is below the engine internal temperature. In flight, these particles will immediately melt if they go through the engine, and going through the turbine, the melted materials are rapidly then cooled down on the other side and stick to the turbine vanes and disturb the flight flow characteristics and can plug things and cause non-mixture of the combustion gases, producing little power and even stalling at times, like I said before. As far as the volcanic plume characteristics, notice some of the similarities between a volcanic eruption and strong, severe convective meteorological type storms that occur. Eruptive volcanic plumes occur in numerous forms, as many forms as there are volcanoes, really varying in height and intensity, duration, and style. The thing that's worst with them is that they're not predictable, like at least meteorological thunderstorm formation is somewhat predictable. We usually have a forced jet that occurs at the vent surface that controls the mass and heat flux. These explosive characteristics of volcanoes themselves are manifested from the actual fragmentation of the magma with various eruption-type mechanisms mixing with that of a high-speed jet that issues from the vent itself. And then as it moves upward very rapidly in a short period of time, you get the umbrella region formed, just as you do with severe convective activity that spreads out on top of the column. And the convective columns themselves generally don't extend above the middle stratosphere, but you can see this overshooting top poking up quite a bit above the tropopause in this particular situation. Some of the eruption height and tropospheric instability can make a big difference in the type of eruption that you actually get. And that's one of the reasons that we have a goal here to determine the eruption height and to successfully monitor and forecast the volcanic ash dispersion from the strength of the eruption, but we need to have good observation platforms to obviously do that. In this case, the plume height, like meteorological convection, is affected by wind shear and atmospheric instability. Relatively weak eruptions in moist tropics can trigger deep convective columns, 15 to 20 kilometers in some cases, due to the extreme instability, and that's just from a weak eruption. Given the same eruptive intensity, relatively dry, stable, polar, subpolar environments will generally produce lower eruptive heights, and this makes sense when you think of it in terms of looking at the atmospheric conditions with the sounding, than the moist, unstable tropics. As a matter of fact, there's usually differences between 8 and 10 kilometers at times between eruptive heights in the tropics being very, very high, with those up in the drier polar areas being relatively low. Also, a higher proportion of volcanic clouds will reach aircraft cruising levels in the moist tropics, obviously because of this, than in the drier, more stable poleward environments, especially in the wintertime when you have tropopause levels that are very low. And eruptions at higher latitudes and drier atmospheres are less likely to rise to cruising altitudes as they gain their energy mainly from the volcanic source itself and not much from the atmosphere, where down in the tropics you are actually gaining energy from the instability in the atmosphere itself as the eruption process and the clouds form in the moist tropical air. Just something to keep in mind as far as relative differences in the regional, local conditions, and depending on your latitude. Right here, we're looking at the vertical growth and lateral expansion of an ash plume that happened on St Helens eruption back in 1980. And the vertical growth of the ash plume itself versus the lateral expansion of the ash plume, this is exactly why we have the need for speed when it comes to observation, detection, verification, and warning in situations like this, and the fact that you mix that with an unpredictable situation often at times. In this example, Mount St. Helens eruption, this was data given to us from Boeing. It only took between 6 and 8 minutes for the ash plume to reach between 30 and 40,000 feet in elevation and to extend horizontally away from the volcano up to 27 miles. So by the time I got here, it was already 27 miles away from the vent itself, and that was in less than 10 minutes. So you can see the lateral expansion, of course, it would extend greatly with given a longer period of time and if the eruption process continues. So you got to keep this in mind. It's a very difficult process. Here's another answer as to the why of all this, as there are nearly 500 airports that lie within 100 kilometers or 62 miles of active volcanoes. All the active volcanoes are shown here in red in this particular situation. Here's a close-up view of the North Pacific active volcano region, which has over 100 active volcanoes, which is about 20% of the world's active volcanoes. And, of course, the North Pacific air routes lie over this area. As a matter of fact, in the last 30 years, 15 aircraft have been damaged in this area alone by volcanic ash clouds. Over the same period, worldwide, 80 such encounters have happened, causing hundreds of millions of dollars in damage and loss in revenue. Fortunately, no fatalities at this point have occurred, but the growth rate in air traffic over volcanically active regions, such as this area in the North Pacific, is increasing and can only increase the chance of a deadly encounter occurring at some time. Here's another look at the actual common flight routes over this highly active volcanic region. You can easily see the need for advanced observations and forecasting skill in these areas where you have frequent volcanic plume movement. As a matter of fact, each year about 5 eruptions occur in this region along the 2,400 nautical mile arc from Alaska to the Kuril Islands down here south of the Kamchatka Peninsula. These clouds are, occur in the Ring of Fire area, so having eruptions is not anything unnormal, and that's just on an average year. Each year, with those 5 eruptions, you tend to have about 4 days where volcanic ash is present above an altitude of 30,000 feet, which is where most of the large jet aircraft fly. So you can see, again, the need to answer that question why, and why we need forecasting skill, and why we need to remain aware of what's going on in our regions. And then there's the hazards to the airports themselves. In addition to posing as a hazard to in-flight aircraft coming in for landings, volcanic ash can disrupt airport operations with local to global consequences for both life and commerce. Worldwide, as we said before, 500 airports lie within 62 miles of an active volcano, and the primary volcanic hazard of these airports is ashfall itself, which causes not only loss of visibility, slippery runways, but also can cause structural damage and contamination of ground systems, and even hurt stored aircrafts that are stored along the slippery runways or in the hangars. Ash in the airspace around the airports also can cause the airport to close itself, and because of the catastrophic consequences associated with eruptions, can also cause the closure of alternate landing sites, making it very difficult to find a place for any aircraft to land at a given time. In this photo here, an American Airlines jet was parked at the tarmac of a ash-covered tarmac from the eruption of the Pacaya volcano just outside of Guatemala City in Central America. And this was in May of 2010. This actually forced the closure of the international airport, and there were a few people killed in this particular incident from the eruption of the volcano itself. It didn't have to do with aviation in this case. It was actually projectiles coming out of the volcano, which actually killed a few people. So something else to keep in mind. Volcanic hazards to airports. The primary hazard, which we stated, was ashfall, which can cause the loss of visibility and slippery runways, and also infiltrate communications and electrical systems, interrupt the ground services and damage buildings, parked airplanes, and hurt, of course, engines, which we talked about before. At least 101 airports in 28 different countries have been impacted on 171 separate occasions between 1944 and 2006 by the eruptions of just 46 separate volcanoes. Accumulating ash does not simply disappear like snow does, so you have to, or blow away like leaves or other debris, but it has to be disposed of in a manner that prevents it from being remobilized into the air by the wind and or aircraft during the cleanup process itself. On the average, 5 airports every year, we mentioned this before, impacted by volcanic activity just up in the northwest part of the United States or the Northwest Pacific. Primary hazard is ashfall, as we stated before. The accumulation of anything more than just a trace amount requires the full removal of the ash in order for the airport to resume full operations, and it must remain closed until it actually gets those trace amounts or greater off the runway. Indonesia has 7 volcanoes whose eruptions have impacted airports. Here in the USA, we have 5, and Japan, coming in also in a tie for second place, also has 5 volcanoes whose eruptions have impacted airports recently. And now we'll move into the next section covering remote sensing and observations. Here's an interesting photo of ash that was blew out from Mount Pinatubo on November 27th of 1991, even though this wasn't taken from a satellite or anything. It was taken from another ground observers of the area. It is a quite interesting photo showing that it almost looks like snow in the region, but actually this is all entirely ash that had been blown out from the volcano. It can take many hours for eruptions occurring in remote regions to be recognized and addressed at times, and while some relatively mild eruptions occurring in remote areas, they can go undetected for hours or even days. Volcanic ash can reach commercial flight levels, in some cases up to 30,000 feet in 5 to 10 minutes, which we saw before in the schematic, and remain airborne for several days. Weak eruptions spreading optical thinning of the plume or background non-volcanic clouds, formed from convective activity, can significantly reduce the visible satellite signature at times, making it very difficult to discern an ash cloud from a meteorological cloud. Also, wide variability in composition and structure of the ash itself can also cause various detection problems. Ash cloud height can be a particularly tricky problem at times, especially when the plume is very optically thin. Also, radar in an aircraft is ineffective in locating ash clouds at this time. Why is remote sensing so important? Well, here's a look at a map of major flight routes of the world together with a plot of the active volcanoes of the world. The black triangles, like up here in the northwest part of the CONUS, show volcanoes with some sort of monitoring currently going on, and that's formal monitoring. However, all the blue areas that are highlighted around here are areas without any structured monitoring program at all, which shows the necessary need for a good remote sensing kind of program in order to detect these eruptions in suitable amount of time in order to prevent accidents from aircraft flying along any of these flight routes. Here are some of the observation platforms that we're going to be covering in this remote sensing section. We'll be starting out with observations by satellite, showing visible imagery and how important it can still be after all this time. We'll be looking at split-channel reverse absorption, 3.9 micron imagery for detection of hot spots and ash clouds. We'll be looking at methods for following SO2 in the air using OMI infrared measurements that occur in the 7 to 12 micron range. And we'll be looking for other image enhancement techniques with satellite imagery that will help us identify and follow ash plumes over a period of time. Then moving down in the atmosphere a little bit, we want to note how important observation by aircraft can be, all visual by cameras, and also the issuance of pilot reports and how important those are to keep other pilots and other aircraft out of danger. Also, moving even further down towards the ground, we have observations from the ground themselves, including radar, automatic cameras, video cameras, and yes, even personal identification by just a plain human being on his own. First up, we're going to talk about satellite observations, the data, analysis, and the products. Some of the more important points for remote sensing by satellite, of course, the biggest one is there is global coverage. It allows for tracking of plume movement both during the day and at night, provides information in remote locations, and can be used in conjunction with other information to determine plume height and probable or forecastable plume movement. Also important is the monitoring of thermal energy emitted by the volcano by looking at different wavelengths, mapping of the surface, deformation of the volcano, including topography and topographic changes, or the geodetics, aid in producing temporal and spatial distribution of ash and gases produced in the volcanic eruption, and it can help contribute to a baseline data set for quantifying future changes with a given volcano. And also, and last but not least, contributing to model data set that can help produce future movement of the ash or gases in within the models themselves. Here's just a few of the satellite products we'll talk a little bit more in depth about, including the various GOES and POSE platforms, the Europe's Meteosat series, which we often get good data sets from. And within those, we'll be looking at visible, shortwave, infrared, long-wave infrared, and of course the differencing products such as the split window we'll talk about. And then we'll be looking at various other multispectral type of products such as principal component analysis and LROD-derived products, and then finish up with some gas tracing such as the SO2 OMI monitoring instrument. Nothing beats a good high-resolution visible product for sheer impact. Here's a polar orbiter off the MOSE Aqua, giving us an RGB product combining bands 1, 4, and 3 together. This was taken on April 19th, 2010, showing the Iceland volcano and the ash being put out from the volcano right here. You can easily track the ash during the daytime, even around this nice little low-level vortex center moving out and seeing and tracing how the ash is actually moving through the atmosphere. Here's another visible look. This is taken off the Meteosat geostationary platform, Meteosat 9. This was taken on May 7th, 2010. And we can also easily see from this, especially when you animate it, the trail of the ash coming around and moving, and you can trace it over a period of time, match it up to your models, of course, and see how they're doing, and also keep aircraft in real time out of these areas. So very important from that standpoint. Here's a closer look, a good close-up look actually at it. This is off the same platform, Meteosat 9, same image. We're just looking at a close-up view to easily be able to track the ash in this particular situation. And finally, we look at a visible image. This is actually a faux RGB product that was put together from the eruption on Mount St Helens back in May 18th of 1980, 30 years ago, and we still had a good product like this. And here's a good example of the ash cloud poking up through meteorological cloud around this, showing the extreme volatility of the eruption at that period of time. So even back then we had good, decent products to deal with, and this shows the value, especially when dealing with a catastrophic kind of situation that we're talking about here with volcanoes, of looking where the important volcanic ash is rising in the atmosphere. Next up, we have some good visible images taken from GOES 3, again 30 years ago on the May 18th, 1980 eruption of Mount St Helens, showing the progression of ash over a 30-hour time period. This is the initial photograph that we saw before with the false color image showing the initial eruption, and this is the initial time period plus 6 minutes. We'll move out a little bit further. This is the initial eruption plus 1 hour, and we can see that the plume has already moved out a couple hundred miles from the vent itself over just a short period of time. Here's the initial eruption plus 3 hours. Now we see evidence of the ash cloud moving all the way over eastern parts of Oregon and into Idaho, and that's just after 3 hours. Then we move 6 hours out, and we're moving all the way into Montana and even parts of northwestern Wyoming. And then finally, I put up a initial eruption plus 30 hours, and we actually trace the volcanic ash cloud all the way down into parts of Oklahoma, across much of the Rocky Mountains into the Central Plains and down into the Southern Plains even. So you can see the extent of an ash cloud over just a day and a half kind of period. And this, you can also see how this would greatly disrupt air traffic at times, moving both east and west across this country. So it's very important to use all the platforms you can to gather all the data you can, and also put this with the forecast models in order to determine where these things are. This is another reason that we really need to remain aware of these situations, even though they don't happen every day. Here's a very interesting look at high-resolution visible imagery taken from a polar orbiter. This is the Terra. It was taken on July 13, 2008 from the eruption of the Okmok volcano. This kind of visible imagery is very good at detecting albedo differences, especially when it's moving over a nice contrasty surface. It can also be a problem at times detecting ash when it moves over a surface of a similar color, but in this case it works out very, very well moving over the water in this particular situation. Here we have an easy way to track both the steam water cloud moving more off to the southeast than the heavier, more dense ash cloud moving off more to the south, and that's due to differences in the characteristics of the flow at different levels in the atmosphere. We have different shear zones here. At the upper levels, the winds are flowing more to the southeast. At the lower levels, they're flowing more to the south, as in this case down here. And because of the microphysics differences between the two, that's why the ash gets caught up and moves off more to the south. In this case, at the lower levels, because it's heavier and more dense and gets caught up in the flow first, where here we're actually getting an explosive type eruption up to higher levels to begin with, and it's getting carried off to the southeast. And there are other differences, too, because the steam cloud, water cloud in this case, may be erupting from a slightly higher vent on the volcano than where the ash is actually coming out of, and it may be produced at a slightly lower altitude on the side of the volcano also, which may make a difference. So you have to keep those kind of things in mind when you're looking at this, but this is a great use of visible imagery, high-resolution visible imagery when you have it, because you can definitely see the different characteristics between the different flows and compositions right off the bat, and you can tell where and what's most dangerous in these cases. Moving into the slightly longer shortwave infrared region, here's a 3.7 micron image taken from the polar orbiter NOAA 19 from the AVHRR imager, which stands for Advanced Very High Resolution Radiometer. This is of the IFYATLUT Volcano, taken on April 20th, 2010, and here the hot spots from the volcano can be seen with the green, bluish colored areas, the arrows point to them. And such hotspots can be identified through the use of the mid-infrared channels, such as 3.7 to 3.9 microns, as the increase in temperature generally results in a high signal response in this spectral region. That's why it's very good, especially at or near the surface, too. It's good for noting these kind of things. 3.7 to 3.9 microns is also good for detecting ice cloud differences, whether you have water or mixed water ice or ice clouds, and we use it for that in meteorological circles. The intensification of the hotspots in this particular case seem to indicate that the volcano is potentially starting to eject more lava in this case and therefore less ash. So it does have a good use in this particular situation. Here's another AVHRR product taken from the NOAA 18 Polar Orbiter satellite. This is channel 4, somewhere in the 10.3 to 11.3 micron range, taken of the Okmok volcano on July 13, 2008. Long-wave IR by itself can be of great help in deriving cloud top temperature information in this case. And then you put that together with the local regional sounding data, and this can aid in calculating plume heights. Or on AWEBS, you can even use your cloud height algorithm at times to find these. From the data present on this day, July 13th, for Okmok, it was determined that the ash plume close to the islands and the eruption itself was actually topping out at around 25,000 feet on this particular day. Here's another look at a long-wave infrared product taken off a geostationary satellite, in this case the Meteosat 9 out of Europe. This is of the Iceland volcano, and this is the same view in the same time period as the previous visible image that we saw, matching up to the same time period. The important part about here is, although we could trace it in the visible imagery, which is great, in this case we could trace it in the long-wave infrared, which helps us for viewing and tracing, tracking, observing these kind of eruptions at nighttime, so it's very helpful in those particular situations. And now we'll start talking about different ways to put together different image channels in order to highlight ash in the atmosphere. First up, we'll talk about the split window or channel differencing of the long-wave infrared. It turns out that silicate particles have emissivity that's lower at 11 microns than at 12. The emissivity of water or ice particles is just the opposite. It's higher at 11 and lower at 12 microns. Therefore, ash clouds can be detected by this method by the brightness temperature difference. And here's how it looks. So if you have a 10.7 micron image, you subtract the 12 micron image from that, you get a negative value, and the negative value for this is an indicator of ash or dust. Otherwise, brightness temperature of at 10.7 minus 12 microns, if it's positive, that's the indicator for ice and water. So by looking at this is a Meteosat 9 image of the Iceland volcano taken on April 15th, 2010. Ash here is highlighted, the negative values are highlighted here in the white, and so you can kind of see those around the outside of the meteorological cloud that's here in the dark areas, flowing around and into parts of Norway even in this case. Now that's not to say that there's not ash underneath the meteorological cloud here. That can be problems. The meteorological cloud is always a problem in observation of volcanic eruptions, volcanic ash, and those kind of things. So you have to kind of be situationally aware in order to pick these different things out. But anyway, when it does show up, it does highlight very well in this case. This particular eruption in Iceland was a little bit unusual and more explosive than it normally would be associated with volcanoes in Iceland due to the location being beneath 200 meters of thick glacier ice for a while. The ice melted and gushed into the crater of the volcano itself, causing it to become explosively volatile and spew these clouds very high, 2-3 miles into the air at times, which was a very big problem for getting ash up and over the entire European continent for periods of time. So that was a very big problem. So if you can use a differencing product like this to point that out, very, very helpful. Here's another look at it. This is off the Meteosat 9 from a little bit different angle, taken on May 7th, 2010. And this is the 11 micron minus the 12 micron, split window, long wave difference, whatever you want to call it. And here we have it showing the ash here in purple in this particular situation. Seen very clearly, stands out very well among other meteorological cloud. However, you have to keep in mind what's going on in the atmosphere around you, so you want to know the vertical profile of the atmosphere, get soundings in around the area if you can, because if you notice up here, in and around the higher latitudes and stuff, you see a lot of other purple areas, and this is not ash, but channel differencing tends to point out stable areas where temperature inversions are occurring at the surface at times, if there's no cloud or even on top of a cloud, and it'll show up as a negative difference, and the same color will show out. So you have to become situationally aware in these cases and just know that, yes, there's a volcano erupting now. Now I can follow it as ash. If you're up here at the North Pole, no, there's no volcano erupting up there, or it hasn't been days and days and days, so there's probably not any reason to suspect that any of this up here is volcanic ash. And finally, we take a look at the Okmok volcano. This is a polar orbiter nose 18 AVHRR, split window, differencing channel. Boy, that's a mouthful right there. Showing the negative differences here in blue, where the ash is around the cloud. Now you can see the eruption column coming out of it right in here, which is a water column from the eruption itself. Now again, that's not to say there's not some ash underneath, and certainly close to the volcano in this area there would be ash associated underneath. And we can't quite see through the meteorological cloud here, but on the edges we are able to pick that up. So if you're in a watch or warning kind of situation where you're trying to determine where the ash cloud is, it's very hard, very, very hard. You know, does it occur in this whole area here that's outlined? Just because we can pick up ash in between, we have to almost assume that it would be or could be through this whole area. So you might want to put out watch or warning that would consider that case. But on the other hand, as we get better, our models get better, our observation platforms get better. Maybe perhaps in the future we may be able to differentiate between a non-ash area with that of an ash type area to help the flow of aircraft in and around certain regions. And now we take the idea of combining different image channels together to get different products that we can help us trace volcanic ash a little bit further. All these images that are coming up are thanks to Don Hilger here at CIRA, who works for NOAA and NESDIS. This idea, in this particular case called Principal Component Imagery, or PCI, it actually extracts the principal or wanted features from an image. These features are then integrated into a single image, which we'll see in a moment, to compile a great deal of information from a large number of sources and bands into a lesser number of bands to give us what we are looking for. In this particular situation, we're talking about GOES 11 satellite. We're using 5 bands. PCI, Principal Component Image 1, looks very much just like a regular long-wave infrared product, but it's actually a combination of 5 bands, but in this case it's long-wave infrared dominant. And you can see that it looks pretty much like an infrared band you would expect in the 11 to 12 micron region. Also, there's not much of a way to tell the difference between ash and water cloud in this particular situation during the eruption of Okmok. Now we look at another view. This is PCI 2, which is a visible dominant. Again, it's a combination, a 5-band combination, but it's visible dominant. Now here you can get an idea of where some ash is poking out in and through, maybe speckled in and through some of the water cloud or steam cloud or gas cloud from the eruption. So you do get a little bit better idea here that there's some ash involved. Now we go to PCI 3, which is a shortwave infrared dominant. And again, here we're actually seeing something a little bit different. These water cloud areas are actually highlighting here, showing as very white in this particular situation, but they're also co-located with what we're seeing as possibly being some ash here. So there's a combination of the two, ash and water cloud going on. So now we have a couple of things. Now we go and look at what we just talked about before, the split window channel, which is the 10.7 micron minus 12 micron, and we come up with this, and it shows the volcanic ash here in the darker areas. So now, if we're going to take these 5-band products, each with a different type of dominant signal here, long wave, visible, short wave, and then the split window, which of these would you want to use to combine into a single product to really make that ash stand out? Well, all 3 of these here in the corner, the short wave, the visible, and the split window, all have value. They're all showing areas co-located with ash in some cases. The only one that doesn't show much use is the long wave infrared here, so we probably are not going to use that in the later combined PCA, or principal component analysis product, and we'll see that in just a minute. Okay, here is a loop of the previous 4 PCI channels we were just talking about, and keep in mind this is the long wave dominant product, this is the visible dominant product, this is the short wave infrared product, and this is the split window. And again, we can see the utility, although we're seeing indications of an eruption, of a cloud around in all of these. We want to keep in mind that the ash cloud isn't everywhere, and the long wave here in this particular situation gives us subtle, let me go ahead and stop that for a minute, subtle indications that we have ash here, but they really don't stand out very well in and around the rest of the steam, eruption, volcanic, meteorological cloud, eruption cloud, whatever you want to call it. So we're not going to pay as much attention to this. However, these others, the visible, the short wave, infrared, and the split window, all have good signal indications lining up where the ash is too, although here it's indicating that water and ash are co-located, which is an important feature, and we want to keep that in mind that can often happen. Okay, now we're going to do some principal component analysis using the principal component imagery we just talked about. We previously saw 4 of the 5 bands. We determined that 3 of the bands, minus the long wave infrared imagery, were the best. They showed the best ash results, and we want to now take that and compress all that information of the 3 bands into a single synthetic imagery. In this case, it's an RGB imagery we're showing in color. The idea is to get rid of redundancy, and only 3 of the 5 bands were needed to extract the most information. So we're going to combine PCI 3, which was the shortwave infrared, with PCI 2, the visible, with PCI 5, which was the split window. Put them all together, give them each a little bit different weighting. We're going to color them, synthetically color them in red, green, and blue to come up with this synthetic colored image. So when we're done here, the ash is actually showing up in the yellow and oranges, which we can see highlighted here on the edges, and we also see indications that there may be some under the water cloud here. This is very important, very easily to identify the ash in this particular situation, although if there was thick meteorological cloud over the top of this, it still could make a difference or difficult. But in this case, it's a very good way to take the best of all these different channels, or in this case 3 different channels, put them all together and give us the best enhancement we can possibly find, and we can trace this over long distances, over a long period of time, over several days too. Here's a final look, animation of the eruption from Okmok, showing the PCA analysis and where it's going over a period of time, and how easy this kind of system, at least during the daylight hours, since we are using visible imagery as one of our components, makes it easy to track the ash in this case, which shows up as the brownish orange color out here. But it shows it very easy way to track ash in this particular situation by taking the best of the best of the best out of each of the different kind of imageries, putting them together, weighting them a little bit, giving them each a different color, and then we come up with this nice color image. So just keep that in mind. One problem we do have, this is with GOES 11. We lost some of the ability to get a split window type differencing product out of the newer satellites, GOES 12 and 13, but our ability, and that's because we lost some channels, but our ability to do this will return once again with the GOES R series of satellites. And now for another ash detection product or combination product, the so-called 3-channel product or LROD product, which is brought to us by our friends at NESDIS, Ken Pryor and Gary Elrod. This combines data from the shortwave infrared channel with 2 long-wave infrared channels to give us the benefits of both split window ash detection and the 3.9 micron hot spot detection, both of which we talked about earlier. Here's an example using GOES 12. On the left here we have the visible imagery during an eruption over Sophry Hills, just showing us the location of the volcanic ash. And here on the right, we see it lined up with the same detection of the 3-channel product, showing us the location of the volcanic ash. Now it looks a little bit lower in resolution here on the right, but the idea here is that you can use this product 24/7, and is especially useful for nighttime detection of hotspots and volcanic ash. The way this looks in the detection algorithms, this is for GOES 11. Here we have the part where we have the split window detection combined with the hot spot detection. We combine that together, and if we get a value for B that results in a positive value, that's for volcanic ash. That tells us that we've got volcanic ash. And on GOES 11, since we're able to use the 12 micron long wave channel, that's beneficial, and that's ideal for detecting ash. Now we'll show you the same thing on GOES 12 platform, which is similar but a little bit different. We're still combining the hotspot detection of 3.9 micron channel with the 2 long wave channels here, except that we have to use the 13.3 micron channel in this particular situation, and it's not quite as ideal for locating ash. It's not as effective as locating ash as the band for the 10.7 micron channel, but it can still help you distinguish ash from cirrus, which is very important. So this is a useful product, again, day or night in these situations. Here's a comparative look at 4 different products showing the benefits of multispectral imagery in ash detection analysis. This is from the Popocatépetl volcano in Mexico, the eruption on November 29, 1998. In the upper left-hand corner here, we show the normal channel 4, 10.7 micron image. You can barely make out where there might be some ash coming out from this particular eruption. However, here on the right, upper right over here, we show the 3-channel product we just got through talking about, and it shows you very much how well this product will make the hotspots and the ash detection stand out from an eruption. Down here in the lower left, this is also the split window detection that we talked about, the channel differencing, and you can also see how well it picks out the ash in this particular situation. And here in the lower right also shows the benefits of the reflectivity or fog product. You can even make out some ash detection in this particular situation. But the idea here is that multispectral imagery will really highlight areas where there's ash detection, where normal or single channels will have a very difficult time making out ash. Here's a look at a promising use of MODIS band 26, which is 1.375 microns. This is brought to us by Scott Bachmeyer from the Cooperative Institute for Meteorological Satellite Studies. This was taken July 18, 2008, and is after the Okmok eruption up in Alaska, showing diffuse ash clouds moving across northwestern parts of the Dakotas, across northern Idaho, and into western parts of Montana. This is also called the cirrus detection channel, and it shows some good possibilities of being able to locate diffuse ash clouds also. The idea here is that the 1.375 micron channel is located in the middle of a strong water vapor absorption band, and because the cirrus and ash clouds occur in the upper troposphere and lower stratosphere, they appear bright in contrast to the completely attenuated or black surfaces that you see around here. So you can identify them over those areas, and they appear different in appearance also when compared to clouds in the lower troposphere whose reflectance is partially attenuated by water vapor. So it shows a possible use for this channel and this will be available on GOES-R in the future. Now we have to take a quick look at some ash detection product limitations. One thing that's clear, and it'll be clear throughout the rest of this session, is that water vapor and clouds can present problems in detection of volcanic eruptions, whether you're talking about looking at something through the eyes of a satellite or whether you're on the ground trying to detect volcanic eruptions themselves there. Water vapor in the volcanic eruption itself can result in non-discrimination of ash when it mixes together. Also, in deep tropical conditions, this can mask the presence of volcanic ash or prevent clear discrimination of ash from meteorological clouds. This is especially true for the eruptions of smaller volcanoes that emit ash only into the lower and middle troposphere, such as the Sophry Hills volcano, instead of getting way up there into the upper portions of the troposphere or stratosphere, where it can be detected much easier. Also, important is the modification to the GOES 12 and 13 platforms. We lost the 4-kilometer resolution or the 12-micron band, which was replaced with a lower resolution 8-kilometer infrared band or the 13.3 micron band. In split window detection, this is not ideal. There is some denigration of remote sensing of volcanic ash due to this, leading possibly to the underdetection of thin ash and an increase in the area of false ash warnings, resulting in possible overwarning in some situations. This just can't be helped in the meantime. However, with the coming of GOES 12 in around 2017, the 12-micron band will be restored and become fully operational, and this will bring back the best of all worlds in these kind of situations. But in the meantime, what we have is better than nothing, and this is still a somewhat effective means of being able to warn pilots of hazardous ash clouds in many different situations, so we wanted to keep that in mind. And now we'll take a bit of a look at gas cloud detection using the OMI, or ozone monitoring instrument, which is obviously good for more than just monitoring ozone. This instrument is a nadir viewing near ultraviolet and visible CCD spectrometer that's aboard NASA's Earth Observing System's Aura satellite. One of its missions to detect, track, and measure volcanic eruptions and degassing. It essentially completes global coverage in one day. This instrument also has the ability to distinguish between aerosol types such as smoke, dust, and sulfates by measuring aerosol absorption capacity in terms of aerosol absorption optical depth or single scattering albedo, which makes them excellent for detecting and following sulfur dioxide plumes. In this example here, this is a composite image from August 12th showing the sulfur dioxide cloud drifting over parts of Canada and into the United States from an eruption that actually took place 5 days earlier on August 7th from the Casatochi volcano. This cloud is at a range of altitudes, in this case, from 30 to 40,000 feet, and the various colors represent the amount of gas in the atmosphere, with orange or red being the highest and blues being the lowest. Why do we want to look at sulfur dioxide? Well, one of the things is it can be used as a proxy for ash. Following the eruptions of a couple of volcanoes 20, 30 years ago, it was found that in addition to ash damage, even if you just have sulfur dioxide in the atmosphere, you can get damage to acrylic windows, you can get damage to the paint on the aircraft, and also there is some accumulation of sulfate deposits in the turbines. Whether or not they actually damage the turbines, the jury's still out on that. They also, as we saw from the Hawaiian Islands, they produce pollution in the form of VOG. Here's an example from Okmok eruption on July 12th. This is actually done for July 13th, the following day, showing the drift of the sulfur dioxide cloud around and out into the ocean as it heads its way towards Canada and parts of the United States. Here's a comparative photo from the AIRS platform, which is aboard the Aqua satellite. It uses an atmospheric infrared sounder, or AIRS, and it's not quite as sensitive to SO2 as the OMI, but it does a fair job in detecting sulfur dioxide. It's also good at detecting other gases such as ozone, carbon monoxide, carbon dioxide, and methane. But in this case, it lines up very well over here, showing the same general pattern of where the sulfur dioxide was in the atmosphere a day later as we saw previously over here. So there's good agreement here, which makes it verifiable as far as the track of the ozone in this particular situation. So you want to use as many different platforms as possible to get the best possible idea. Here's a look at the Iceland volcano eruption on April 29th, showing the SO2 emissions south of the island, tucked in and just hugging the coast here. And they're not really drifting very far because in this particular case, the winds were very light, as I'll show you here in this sounding, showing the winds very light throughout most of the atmosphere. Actually, even at the upper levels, we're only running 20 to 25 knots. So that's why it didn't drift very far, and it hugged close to the island itself. Next, we'll look at a 5-day group of images starting one day after the main explosive eruption of the Okmok volcano on July 12th. This image right here was taken on July 13th and shows the drift of the main eruptive explosion that took place on the 12th and how it's moved to the south and east over a period of a day. It also shows that the volcano itself is actually still emitting some sulfur dioxide. Moving on to the next day, here we show July 14th. We show the drift continuing to the south and to the east. This portion down here at the base is starting to get caught up in some of the mid and upper level flow. It's a little bit faster at the time, and it's at about approximately 50,000 feet at this point. Moving on to the 15th, this is a composite image, a 2-day composite, showing part of where the drift cloud was on the 14th and where it has moved to on the 15th. This is very good for showing and presenting a spatial and temporal continuity. You want to keep that in mind. Moving on to the 16th, the drift continues to the south and to the east. Now we're getting caught in a stronger westerly flow as it starts to head towards the northeast part of the conus itself, gets stretched out. And finally, a look on the 17th showing, this is all from the original eruption on the 12th. You have to keep that in mind, and showing the position of the SO2 cloud as it moves in and across northern parts and northwestern parts of the conus. So very good. And remember that SO2 is an approximate proxy sometimes for diffuse ash concentrations. You want to keep that in mind. Here's a look at a combined multispectral product. This is taken from Meteosat 9 and showing the ash and SO2 positions over a period of time, and also details why SO2 can be a pretty good proxy for ash, at least for a certain period of time. This was taken from the eruption of the Iceland volcano on April 20th, 2010, when at that time it was emitting fairly large quantities of both ash and sulfur dioxide in the atmosphere. Sulfur dioxide and ash particles differ in their radiative properties, and through the use of suitable combinations of channels, in this case we use 10.8 microns and 12 microns, get a differencing there. You get ash highlighted here in yellow, taking off to the south and then turning to the east. And then you difference the 8.7 microns with the 12 micron channel, and you get the sulfur dioxide here in the blue, where you can see they're fairly co-located for a while close in, but then towards the end they start to drift apart, and this can be very difficult as far as forecasting and detecting these clouds of ash, just because they start to part ways later on. You can't always be sure that ash isn't associated with the SO2 cloud, so sometimes you have to just overwarn, and you cannot classify ash-free areas as being safe just because you can't see the ash in this particular situation. You'd have to go with whatever you could happen to detect best, and this is usually SO2 over longer distances. Here's a schematic that looks at the combined results of two model simulations of the climactic 1991 eruption of Mount Pinatubo. In this particular situation, one model depicting on the location of the SO2 cloud, the other one depicting the location of the ash cloud. and in this case, noting that they're not exactly co-located, especially in the vertical. We had a maximum column height of nearly 40 kilometers, yet most of the ash leveled off and transported at the tropopause or just above it itself, while the SO2 went up much higher to nearly 25 kilometers before being transported over the China Sea. And also you note that the SO2 cloud was only transported in one direction, which was co-located with part of the ash cloud and not the other. So if you're going strictly by SO2 location, you would not have been able to identify this area of ash concentration unless you could actually detect it by other means. So you want to keep that in mind. Also, there's a difference in the vertical that if we can locate the positions vertically, we notice that the airspace below this would be nearly free of ash. And there would be some speculation that there could be ash down here, and some would be falling out, of course, but the heavier concentrations would be located in this area up here near the tropopause, at least for a certain period of time. If you're going by the location of the SO2 cloud by itself, which was much higher, you would have missed a lot of the free space between the two and also above it and below the ash cloud. So there's a lot of problems here in both the horizontal and the vertical here, locating the positions of this. And if you had any other stable layers in the atmosphere, inversions here, and you actually had some of the ash transport lower down, or you had several layers of ash going on and maybe a little bit lower position for SO2 cloud, you can see where the problems arise, and we want to be able to eventually detect these different layers in the vertical so that we can actually move aircraft through the different clear areas instead of just shutting off the entire airspace like they do at this point. And now for a look into the future with the GOES-R platform, which should be around in about 2017. A suite of GOES-R products will detect and monitor volcanic ash as well as sulfur dioxide, which often is co-located, sometimes not. We saw that with ash in the volcanic clouds. Current GOES operational volcanic cloud products are qualitative, primarily due to sensor limitations. Improved spatial resolution and a large selection of spectral channels will enable GOES-R ABI, or Advanced Baseline Imager, to generate more advanced quantitative volcanic cloud products. The SO2 detection product will automatically detect volcanic clouds during very early stages when an ash signal is generally obscured by liquid water and ice. The volcanic ash product will provide objective estimates of ash cloud coverage, height, mass, and particle size, which are necessary to issue segments in the case of advisories for aircraft, and accurately forecast the dispersion of the ash clouds themselves when put into models. The GOES-R volcanic ash and SO2 detection products will be generated from infrared radiances, which are day-night independent. ABI channels centered at 7.3, 8.5, 11, 12, and 13.3 micrometers will be used in all the algorithms, with the 8.5, 11, and 12 micron channels providing information on cloud particle size and composition. The 13.3 micron channel will detect ash cloud height, and the 7.3 micron channel will detect SO2 clouds. These algorithms are unique because they account for background conditions such as surface temperature, surface emissivity, atmospheric temperature, and water vapor on a pixel-by-pixel basis. Consideration of background conditions results in greater sensitivity to thin ash located in the atmosphere and consistent algorithm performance from the tropics, where you can have water vapor problems, all the way up to high latitudes. You get that consistency all the way across. So in a nutshell, here are some of the benefits from the GOES-R volcanic products yet to come. The advanced spectral, spatial, and temporal resolution of a GOES-R Advanced Baseline Imager will be utilized to generate a complete set of volcanic cloud detection and monitoring projects, resulting in improved air and ground safety as well as economic savings. Also, the GOES-R products will be used to improve modeling of volcanic ash clouds, which will allow for more accurate cloud dispersion and ashfall forecasts. Here are two good examples of future GOES-R volcanic ash products. based on the eruption of Mount Redoubt back on March 23, 2009, brought to us by Jim Gurka, Steve Goodman, Mike Pavlonis, and Gary Hufford. This example actually simulates what we would be getting with the GOES-ARP platform in the form of ash loading here on the left, which is critical. We must know the concentration within the atmosphere and where it's located horizontally, with ash height here on the right, showing the relative locations within that horizontal view and where the ash is located. This is critical for being able to fly aircraft in and around an area where a volcano is currently erupting and getting them in and out of around an area safely. Moving down in the atmosphere to other observational platforms, we come to aircraft observations. Here's a photo of Mount St. Helens taken from aircraft in May of 1980. The airborne perspective gives you great perspective and great viewing distance and is also a means of remote access. However, there is limited nighttime use, and again, like any other platforms, clouds can get in the way and obscure observations. Also, you have to remember that pilot weather radar is not sensitive to volcanic ash, so there is some danger involved if you get too close. Moving even lower in the atmosphere, down to the ground that is, there are ground observations. This can be a great source of remote access for direct observation or even indirect observation by automated video cameras. In addition, this technology is usually a little bit on the lower side and a bit cheaper. You also have the power of local and subjective interpretation. Nighttime observations are even available in the form of thermal infrared heat cameras with automated systems. However, this technology is usually a bit more expensive. However, water and ice cloud and other poor visibility can obscure volcanic clouds just like any other observational platform, and it also requires a locally developed infrastructure and good reliable communications, and is sometimes prone to vandalisms with the automated systems. Here's a good observation of a turbulent mammatus ash cloud actually formed from Mount St. Helens on May 19th, the day after the main eruption. This is over Ephrata Airport in Washington. This not only can tell you a lot about the volcanic eruption itself, but also about the atmosphere in this particular situation. And here's a look of the streets in Yakima, Washington on May 18th, if you were lucky or unlucky enough to be there. Again, observation, direct observation, subjective observation. A picture is worth 1,000 words. For more high-tech ground-based observational tools or remote sensing platforms, we have radar observations. The ability of the radar to provide near real-time updates on the position and altitude of volcanic ash can be vital in providing timely and accurate forecasts and warnings. One of the most significant contributions made by radar is in the short-term aviation forecasting. These observations, in tandem with pilot reports, are used to ascertain the vertical extent of ash clouds and issue timely advisories to the aviation community. The ability to track the volcanic ash in the short term is also vital in issuing timely and location-specific volcanic ashfall advisories. Radar is good at measuring height and position and can help the forecast projection and the timing of the ash plume, especially of the larger particles in the ash cloud. However, you need relatively expensive ground radar stations and in the right place, or expensive portable units that can sometimes be hard to get to a good location, and even these all have limited ranges. It will not detect smaller particles very well unless it's in sufficiently dense quantities. Observations can also be obscured by heavy rain, and it requires advanced local infrastructure and excellent communications must be well staffed at all times. It is also very important to obtain radar information right away if possible. When an eruption is in the vicinity of the radar, that information is immediately used in the initial eruption height for determining SIGMET advisories and to put into model runs. Here's a good example of early detection of a volcanic eruption with radar. This is from the April 5, 2005 Anatahan volcanic eruption in Guam from Tim Hendricks at the National Weather Service Forecast Office in Guam. This shows a 0.5 degree reflectivity image showing 50 to 55 dBz observed at 30,000 feet initially. This information would be used as an initial starting point with the models. A few minutes later, we move up at a 1.5 degree reflectivity image and are showing 40 to 45 dBz, showing up at just over 50,000 feet. Again, this would be put into the models and also made part of the SIGMET message, which would be issued for the area. And then, of course, we want to put the two together. This is a combination image of infrared 10.7 micron imagery combined in AWIPS, which we do a lot of times, with the reflectivity images to give us an image that can be of much more value. Here we show the values in the middle where the initial eruption, the most strongest part of the eruption, the largest particles with the ash are. However, the radar cannot pick up the more diffuse and smaller particles, and that's picked up with the satellite imagery itself, as we show at the low to mid levels, a drift off to the southwest, and even at the upper levels, we're showing a drift down towards Tinian and Saipan. So this can be very useful when you put all these together to give us an idea of what we need to get into the models to begin with, and also what we need to put into the SIGMETs to get that information out in 5 to 10 minutes or as quickly as we possibly can. A bit more exotic perhaps than radar, but ever more useful, at least at short ranges, and if they're available, is LIDAR, or light detection and ranging. This is the visible light analog of radar. Very short laser pulses of light are sent into the atmosphere and scattered back to the LIDAR by gases and aerosols in the air. And from the measurement of the time out to the scatters to the time back, the position, concentration, and other information on the properties of the scatterers can be determined. LIDAR instruments observe aerosol particles in the air by transmitting an optical pulse and observing the radiation backscattered from the particles, and are capable of detecting aerosol layers in the structure, which makes them very, very useful in order to find these layers. LIDARs have detected relatively thin layers of volcanic ash, both bottom and top heights. LIDARs can be used on either surface-based, they can be satellite-based as on Calypso, and even airborne on aircraft, or even dropped within dropsondes at times. Within the U.S. and Canada, there's only a minimum number of surface-based LIDARs available at this time, and most of them are in western regions. Here we have an example of the polarized signal above Palaiseau, France, on April 16th from the eruption of the Iceland volcano, showing the main part of the ash cloud being up around 6 kilometers initially, right in this area, and then over a period of time, over the next 6-7 hours, drifting downward to around 4 kilometers. Here's another example a little bit later. This is the next day, showing a very similar type of situation. We can pick up the very diffuse clouds, the heavier concentrations coming in at around 3 kilometers early and slowly drifting down in height to just around or just above 2 kilometers over the period of a day. We also see a generalized area of very diffused ash over much of the area. And just so you know, these areas up here a little bit higher are actually cirrus clouds that the LIDAR is observing. Here's a quick synopsis of the observational strengths and weaknesses of some of the various remote sensing platforms, starting with satellite. Visible satellite, very good at high resolution detail, detects albedo differences, good in contrasty situations. Weaknesses, and this is going to show up with all the platforms, or nearly all of them. Water and ice clouds can obscure volcanic cloud. Also, you can only use visible satellite daytime. Ash may be difficult to discern if it's got very low albedo. It's too diffuse to tell from the background, so you have to keep that in mind. Infrared satellite imagery, very good for temperature-sensitive situations, detecting hot spots. It's also unaffected by nighttime, and that's great. However, water ice can obscure this volcanic cloud again, and observation temperature can be misleading at times. This has to do with the same problem that you have when you're trying to detect optically thin clouds. Thin clouds may have warmer brightness temperatures than actual physical temperature of the clouds. This effect occurs because the satellite is seeing through the thin clouds to warmer clouds or to the warmer surface below. Thus, a thin cloud or diffuse ash cloud tend to have calculated heights that are too low, so you have to keep that in mind. Split window infrared, very good at discriminating ash from meteorological cloud. However, water and ice cloud, again, can obscure volcanic cloud. You also get false alarms from desert areas or from stratospheric cloud areas. And it's possible that water vapor can mix with and hide the ash. This is especially true at low latitudes and in the tropics, so you want to kind of keep that in mind also. Video cameras, this is of course on the ground or could be in the air too. The strengths, you have remote access to direct observations at times if you have good communication or good wire or good satellite communications. However, again, clouds can affect the visibility and obscure the volcanic cloud. It also requires some kind of a locally developed infrastructure that's reliable and has good communications, also prone to vandalism at times. We talked about that earlier. Then there's thermal infrared cameras, good for nighttime measurements, obviously. But again, clouds can obscure this. They are rather expensive. It also requires locally developed infrastructures that are pretty strong and reliable, and good communications, and are also prone to vandalism. And then, of course, there's the plain old direct human observation. This is low tech, but it does have the power of local subjective interpretation that's cheap, and you can even get some nighttime observations out of these. However, again, meteorological cloud, poor visibility, can obscure volcanic cloud. And then finally, we come into aircraft or pilot observations reports. These are great because you have a good airborne perspective. You have a good viewing distance and aspect. You can get a lot of information out of this. It can also use cameras at times if you have them aboard. And there is some limited nighttime use. However, again, clouds and poor visibility can obscure the cloud. Also requires good infrastructure and is rather expensive. And you have to remember it's a little bit dangerous too because the pilot weather radar does not and is not sensitive to volcanic ash, so you have to keep that in mind. And then finally, ground-based radar and LiDAR, great for measuring height and position of larger ash particles in clouds. For the smaller ones, you can use LiDAR. It works well, but you have to be the cloud has to be much closer to your position. Radar will work out to 200, 250 nautical miles, but it only works with the larger particles. These systems are all expensive, whether they're ground stations or whether you have portable versions. They also are not good at detecting small particles, although, like I said before, LiDAR can detect these smaller diffuse particles, but you have to be very close. They have to be nearly directly above your location. They can also both be obscured by heavy rain, and it requires a really good, strong local infrastructure and communication-based network. Here are a few overall things to remember from this remote sensing section. Most importantly, no detection technique by itself works for all cases. Techniques should be combined, if possible, to get the best overall ash cloud detection. Some of the inherent limitations for all detection methods are obstruction by meteorological cloud. That affects nearly all remote sensing situations. Ambiguity in the atmospheric data can be due to the regional conditions, so keep aware of what's going on around you of the Earth in that particular situation at that particular time and in that particular place. And finally, low ash content plumes or very thin ash clouds are a problem. And now we move into the last portion of this volcanic ash session, modeling. Numerical models of ash cloud movement can forecast locations of ash clouds and, in principle, can forecast ash concentrations in a quantitative manner that's not quite possible through the use of remote sensing or other observational methods. However, the accuracy of such models hinges in a large part to their input data, which historically has not been well understood during eruptions. It's the old adage, what goes in determines what comes out. Here in this country, we have two primary models used to forecast ash dispersion. The first is the PUF model. The PUF model is a volcanic ash dispersion model originally developed at the Geophysical Institute at the University of Alaska in Fairbanks by Dr. Hiroshi Tanaka. It was used for predicting the movement of eruption clouds and was spurred on by the eruption of Mount Redoubt back in 1989. The other main model is the high-split model. It's a hybrid particle dispersion model and is the result of a joint effort between NOAA and Australia's Bureau of Meteorology. Dates back to around 1980. The current version is in its fourth iteration, and many updates are planned for the future. A few points to remember in all this as we talk about these different models is that regardless of the particular model used, several types of input related to the volcanic source must be known before a guesstimate from the models can be determined, starting with the height of the volcanic plume. This is the most important volcanic input, and it determines whether ash exists at a typical jet cruise altitude or not, and in what wind fields and weather systems it will be dispersed at. And of course, we can find out a lot of this from some of the observations with the satellite imagery and the radar imagery, etc., that we already talked about. Then there's the mass eruption rate, or rate at which ash is pumped into the atmosphere. Ash concentration in volcanic clouds is directly related to this rate, which ranges over more than 5 orders of magnitude. That's 100,000 times for historical events. The mass eruption rate cannot be determined directly during an eruption and can only be estimated by correlation with plume height. So that's why plume height is so important to begin with. Then you have mass distribution of material in the plume itself according to its elevation. Volcanic plumes are driven upward by buoyancy of hot gases and the air itself. In large eruptions, they pump out so much heat and energy into the air that the ash columns can ascend to over 100 kilometers per hour to an elevation at which the density equals that of the surrounding atmosphere. These rapidly rising columns are unlikely to be bent over by the wind because of all the energy incurred in this, so they form a straight or strong plume that spreads laterally near its top to form sort of an umbrella-type cloud. Most mass is concentrated at this elevation. In contrast, the small eruptions or weak eruptions rise slowly and are easily affected by wind to form or bend over according to the wind and give you these weak plumes. Weak plumes distribute mass over a much wider range of elevation in the atmosphere and make them much more difficult to actually forecast at times. And then you have to talk about the fragment size itself and the rate of fallout. Erupted fragments, which are known as tephra, range in size from meters in size to less than a micrometer. Individual fragments may rise to many kilometers in height and then fall out as they travel downwind. Fragments larger than several tens of microns can fall at a meter per second or faster rate, reaching the ground within several hours, and usually within a few hundred kilometers of the volcano itself. However, micron-sized fragments theoretically fall at centimeters per second or less and stay in the atmosphere for days or even up to a few weeks. The fraction of the erupted mass that consists of these small particles is not well understood because most of our knowledge comes from the deposits that fall around the ash cloud and not the actual cloud itself. It's hard to actually sample ash clouds itself, and it's dangerous for aircraft to do so. First up is the PUF model. The PUF model simulates the transport, dispersion, and sedimentation of volcanic ash. It requires horizontal wind field data as a function of height on a regular grid covering the area of interest. PUF output includes the location in 3 dimensions, its size, and age since eruption of the representative ash particles. It can also produce gridded data of relative and absolute ash concentration in the air and on the ground. The PUF model is a Lagrangian trajectory volcanic ash tracking model developed to simulate the movement of airborne ash in near real time following a volcanic eruption. This model is used right away after a volcanic eruption, or even sometimes before a volcanic eruption occurs, to give an idea what would happen if one occurred on a particular day in a particular place. The model tracks particles through a Lagrangian formulation using a random walk technique. The ash source is simulated by releasing ash puffs at a regular interval continually, and each puff contains an appropriate fraction of the ash mass, and then it's advected accordingly to the trajectory of its center position, and the center position would initially be the location of the volcano itself. The size of the puff in 3 dimensions expands in time to account for the dispersive nature of a dynamic atmosphere, just like clouds do, cloud particles do at times. And the concentrations are calculated at specific points on a grid by assuming that the concentrations within the puff have a defined spatial distribution. The tough part here is that volcanic ash clouds do not act like meteorological clouds, and therefore you can't handle them just by meteorological NWP models themselves. You have to have these more specialized models to handle it. The puff model is mainly concerned with the tracking of young eruption clouds, as young clouds are defined at less than 48 to 60 hours old and are especially dangerous to aircraft since the concentrations are highest during this time period. Here's an example of the puff model that I ran for a hypothetical Okmok volcano eruption for the period of May 4th, May 5th, 2010, had an eruption actually occurred on that day. The student is also encouraged to go to these modeling sites and actually run the models him or herself to get an idea of the type of parameters that need to be input. More information on this can be obtained in either the talking points or the links page that's associated with this session. Here's a first look at the initial eruption plus 4 hours of the Okmok. And you can see how the cloud is dispersed at different height levels and spreading out over a period of time. This is plus 12 hours, plus 16 hours, and finally plus 20 hours. And you can see how well, at least apparently well, the model runs and shows you how the clouds are going to drift and disperse over a period of time. Only verification with actual observational data, or whether it's from remote sensing of satellites or data gathered in person by somebody, can actually tell whether the model forecast is doing well or not, but that's the case with all model forecasts, whether you're talking about volcanic eruptions or meteorological situations. Next up is the high-split model, or hybrid single-particle Lagrangian integrated trajectory model. The high-split uses a mix between Eulerian and Lagrangian approaches, with advection and diffusion represented in the Lagrangian framework, but the actual concentrations of ash calculated and represented on a fixed grid, which is the Eulerian part of the equation. The transport and dispersion of the ash cloud itself is calculated through the release in the base model of high-split through the release of a single puff, whereas the puff model we just discussed previously releases puffs continually. High-split, at its simplest, computes the advection of a single ash particle, or simply its trajectory. The newest high-split, high-split 4, actually combines both the puff and the particle methods together, assuming a puff distribution in the horizontal and a particle, or the older high-split, distribution in the vertical. In this way, there's a greater accuracy of vertical dispersion parameterization of the actual particle, and you can combine that with the advantage of having an expanding number of puffs represent the ash as the spatial coverage of the ash actually increases over time. The high-split model is particularly useful in predicting ash plume concentrations as they move forward in time. Whether we're talking about high-split or the puff models, you have to think about dispersion models on the whole, and when they're used operationally, they have a set number of parameters that can produce either over or underestimates. They are good for first guesses, but you want to keep in mind that they may be over or underestimating the actual amount of ash in the air at any one time. So it's standard practice, particularly in the United States, for the VACs to compare the model's output to what they can see or infer from satellite interpretation, or sometimes if they have direct observation and measurements from aircraft, etc. This is a quality control that sometimes produces, or almost always produces, the best combination of forecast tools with the observed volcanic ash at this time. This kind of assessment is done qualitatively and on the fly, and is crucial to the issuance of volcanic ash advisories. Here's an example of an ensemble trajectory forecast from the high-split model. This was run for May 5th, 2010 at Yellowstone as if the supervolcano had gone off. This is a 48-hour forecast, and it was initialized by the WRF 12-kilometer run. The trajectory ensemble option starts multiple trajectories from the starting location, in this case Yellowstone, and each member of the trajectory ensemble is calculated by offsetting the meteorological data by a fixed grid factor. This results in 27 different members for all possible offsets in 3 dimensions. So it's just tweaked a little bit. The advantage to the ensemble method is that it gives a decent approximation of the plume using a group of trajectories together, since a single trajectory cannot properly represent the growth of an ash cloud when the wind field varies in space and height, as this simulation shows. This simulation is instead conducted using many different ash particles with all separate trajectories, which gives a good approximation of where the plume would go in a 48-hour period. Obviously, the low-level winds starting off early on out of the east, but as it's lifted up over a period of time, it gets shunted off to the east or southeast through the 24 to 48-hour time period, which can give a good idea of where areas are going to be affected next. Here's an actual example of an ash layer dispersion forecast run from the high-split model done back on April 27, 2010. The Iceland volcanoes represented here in the black triangle. The pink areas that you see flowing out of here are the actual visual ash that's being forecast. And if you can see ash, it's a bad thing. We also are noting that this is at different levels. This is surface to 55,000 feet, and then up here surface to 20,000, 20,000 to 35,000, and 35 to 55,000. And we're reading from left to right, left being the earliest time, and then we can see the progression of the ash forecast over a period of time here. We move on into the 30 to 40-hour time frame, and we can see the extent of the ash cloud reaching into over Europe and much farther in over 40-hour periods. You can see the extent of the forecast, visual ash in this case. The high-split model is also particularly useful at producing mass dispersion or concentration forecasts. Here's an example from the Iceland volcano, again run back on April 26th of 2010. And the examples that will follow just show relative concentrations of mass units, whatever it is that you happen to pick, per cubic meter in this particular situation. So they're very good at least showing where the highest concentrations overall. This is qualitative, not quantitative. And here's an actual look at the 30-hour forecast itself as we move forward in time. We'll start this off. You can see the highest concentrations being right at or near the volcano, represented here in yellow. It's a little bit hard to see there. And then as we progress in time, you see the plume reaching out and moving over the ocean and towards parts of Europe itself, with additional clouds later on. But the idea here is that you can follow these plumes. You can see where the heaviest concentrations should be. You can get perhaps verification on the actual concentrations and match these up a little bit better. The mass units can be whatever you want them to be. It's all relative. And now we're going to look at a particle dispersion forecast from the high-split model over the same time period for April 26 for the Iceland volcano, which will give us a little bit different vantage point of looking at how things are, and also we'll have the advantage of looking at a cross-section in this particular case. Here's an actual look at the 30-hour particle dispersion forecast from the high-split model for the April 26 time period, which matches up with what we saw in the mass dispersion forecast previously. I'll go ahead and animate this forward, and you can see in 3 dimensions here, by looking at the plan view above and the cross-section down here, we can get an idea of where the lower-level particles are being dispersed off to the west and the southwest, while during the explosive part of the eruption right over the volcano itself, anything that reached the higher levels, say above 3,000 meters or so, got lifted off to the east and eventually off to the northeast over the Netherlands. And now to mention one final model that you may run across here in North America, the CANERM, or Canadian Emergency Response Model. The Canadian response model is a 3-dimensional numerical transport and dispersional model that calculates advection and diffusion, but also simulates wet and dry depositional processes. The CANERM was initially designed to model the transport of radioactive contaminants in the case of a nuclear attack. However, it's since been adapted for volcanic ash and is now used as an emergency forecast tool for predicting the movement of volcanic ash that may threaten Canadian airspace. The CANERM is a fully operational model that the Montreal Volcanic Ash Advisory Center uses and operates as part of the Canadian Meteorological Center. Daily forecasts are produced every day for active or potentially active volcanoes and are ready to be administered to the proper aviation weather forecasting authorities if needed. This example here was run for 3,000 meters and above as a trajectory forecast. You can see how, if you remember back to the particle distribution you saw before, above 3,000 meters, that the ash cloud was actually getting shunted off to the east over the Netherlands type area. This is the way it's showing here too. Here's an example of the trajectory forecast from the high split model for the same time period, showing, even though this is a little bit different mapping look than the CANERM was on, it shows the same thing as the forecast of the trajectories of the ash plume actually over the Netherlands and into Europe also. Although we'll talk much more about the Eyjafjallajökull volcano from Iceland, the eruption during 2010 in part 2 of Volcanoes and Volcanic Ash, I thought we'd go through a few of these conditions, looking at different observational platforms represented for the eruption on May 7th, 2010, just to sort of rehash what we've talked about as far as satellite imagery goes. Here's a look at some visible images put together in the loop from Meteosat 9 satellite in Europe, showing the May 7th, 2010 eruption, the volcanic eruption off the coast of Iceland going on right here. And you can see the trajectory of the ash cloud actually moving off to the south and then shunted off to the southwest over a period of time. Of course, you could take this information and put it into the models and also match the model projected forecast with what you're seeing here at the time to get a little bit better idea what's going on. And now we'll take just a little bit closer up view of the same visible imagery on May 7, 2010. Here's a loop and close-up of the same eruption, showing the location of the volcano just on the southern coast of Iceland here. And you can easily see the volcanic ash plume here, one trailing off to the south-southeast. At the lower levels, actually, the plume is moving off to the southwest. So this shows how difficult the forecast would be to cover a large area of time. Just where is the volcanic ash in this particular situation, and how much of this area would you have to put an advisory out for? Same view, same satellite, same date, May 7, 2010. Different sensor. This is the long-wave infrared sensor in this particular case. And here's a loop of the actual infrared imagery from that day. And you can also see that even in the infrared, and this would especially benefit you at night, you can follow the track of the volcanic ash plume until it mixes up with the clouds down here also. Following up the visible and the long-wave infrared imagery loops that we just saw, now we'll look at the ash product, or the long-wave differencing, or the split window product, however you want to look at it, and show you the benefits of the multispectral type approach. So again, here we have from Meteosat 9 a look at the 11 micron channel minus the 12 micron channel, or long-wave difference, or split window, giving us the negative or purple-colored areas over here. It's very easy in this case to trace the ash, even when it mixed with meteorological clouds and trails off to the south and southwest, where we were losing that in the visible and just the long-wave infrared by itself. And now we'll look at a few hypothetical model runs from over the CONUS using the high-split particle dispersion model, and we'll run for a 48-hour time period between July 21st and July 23rd, 2010. I just picked that one out of the air, so it's nothing special. And for these 5 areas, Mount Lassen, Mount Shasta, Long Valley, Mount Rainier, and Yellowstone, it's a good idea to have practice every once in a while running these models, to be familiar with the models. You can use the online versions, which you can get off our links page, or you can go there and actually download the models onto your computer systems themselves and run them at any time. It's a good idea, again, for practice. If you live in an area that's prone to volcanic eruptions, not a bad idea to pick a mountain or two and run them every single day, just in case. These models are also good at handling particle dispersion for forest fires, for planned burning, and for pollution forecasts within cities. So keep that in mind. First up is Mount Lassen in Northern California, which is the only other Cascades volcano to erupt. recently besides Mount St. Helens. It last erupted May 22nd, 1915. And here's the entire 48-hour particle dispersion forecast for Mount Lassen, again starting on July 21st and running through July 23rd. I'll go ahead and step through this. We can see within the first 6 or so hours, we've got ash forecast to move over parts of northwestern Nevada and into Idaho already. And then as we progress through the time period over the next 2 days, by the time we get to 48 hours, assuming we had continuous eruptions on and off over that period of time, you can see that we had a rather large area affected all the way to the East Coast by this time, all the way up into the upper Midwest, Great Lakes area, and then trickling back down. Now the concentrations seem to be dwindling by the time you get out here, but again, you don't need heavy concentrations of volcanic ash to do damage. We'll talk a little bit more about that in part 2 of Volcanoes and Volcanic Ash. Also in Northern California is beautiful Mount Shasta. Okay, and here's the particle dispersion forecast for Mount Shasta, lining up with the same time period, July 21st through July 23rd, as we saw with Mount Lassen. And they should be pretty similar overall because they're not too far apart. It is in Northern California after all. Go ahead and stop this and we'll run it through, and we can see how the trajectories right away seem to follow a similar pattern, maybe a little bit slower up north at Shasta than they were at Lassen, but overall a very similar pattern. And as we move into the 30 to 48 hour time period, we can also see that much of the western part of the United States and then up into the upper Midwest, although here it looks like it takes the particles a little bit further north into Kansas, and we have a much more diffuse type plume coming over the East Coast by that time. So it's probably would hopefully be much lighter or too light out here to cause a problem. And now we move south, but staying in California all the same, to the supervolcano of the Long Valley caldera. So here's the 48-hour forecast for the Long Valley caldera over the same period of time. The only difference here is that I increased the mass quantity by 3 orders of magnitude since this was a supervolcano, or is a supervolcano, and if it goes, it's going to really go. So we'll step through this one and kind of see what we would expect here. We see similarities in the trajectory, first off, moving through parts of Nevada and into Arizona, but you'll notice that the concentrations and the elevations are much higher and much heavier than they were with the Shasta and Lassen. And over the 30 to 48 hour time period, by the time we get there, we see we have ash flow and particle concentrations much greater over the entire length almost of the lower 48 or the CONUS. So this is something to keep in mind. An eruption of a volcano like this could, in fact, cut one side of the country off from the other very easily. And now we go well up north into Washington and just to the east of Seattle to Mount Rainier. So here we are with Mount Rainier, and even though we're in the same part of the country, the western part of the country, even the northwest, you can see that we have a little bit different type of particle dispersion flow than we did with even Shasta and Lassen in Northern California. Right here, we'll step through it, and you notice at the beginning that the dispersion forecast is actually pushing the ash down south into parts of southwestern Washington and into Oregon, and it takes several days before we get any turnaround or enough elevation to actually start pushing some of the plume off to the northeast. So we have split flow in this case, low level early on flow off to the south-southwest, and later flow during the later 24 hours off to the northeast, causing a problem where virtually much of the south-southwest would be cut off from points north, and Alaska would definitely be affected by something like this. And now we'll move well east of the west coast area into the high Rocky Mountains at Yellowstone Caldera, another supervolcano. As with the Long Valley caldera, I also increased the mass quantity by nearly 3 orders of magnitude, showing the difference between a regular volcano such as Shasta, Rainier, or Lassen with that of a supervolcano, such as the Yellowstone caldera here, if it were to erupt. I'll go ahead and push this forward and let you all see. Notice one thing very quickly. As we eject material very high up into the atmosphere, very quickly it gets caught up in the upper flow very quickly, and in a very, very short order. As a matter of fact, on an order of just 6 to 12 hours, we're already affecting a good portion of the northern part of the CONUS area just in the first 6 to 12 hours. By the time we reach 24 hours, we've effectively cut off most of the northern part of the country and a good portion of southern part of Canada in this case. We would not be able to get flights in or out from most of the continental United States into Canada at all. And by 48 hours, if we had continuous eruptions or off and on eruptions over that 48-hour period, nearly the entire area of the northern East Coast area, parts of southern parts of Canada, and a good portion of the northern part of the lower 48 states would be cut off to air traffic, both cargo and personnel. We would have to deviate flights well west of the Yellowstone region in order to get them into Canada, or even perhaps well north. But by this time, you could actually have some of the more diffuse areas of ash even going that far north, keeping flights from Europe from getting in. Well, that's it for Volcanoes and Volcanic Ash Part 1. In Part 2, we'll be looking at a case study or two. We'll be following the key players and organizations. We'll be looking at how the flow of information goes from one agency to another. We'll be looking closely at the Volcanic Ash Advisory Centers and how they issue volcanic ash advisories. We'll even take a close look at the AVO's Volcanic Hazards program, and finish up with a close inspection of the Iceland volcanic eruption of April and May of 2010, and then finish up the program altogether with a future look at some future products. Welcome to Volcanoes and Volcanic Ash Part 2. I'm Jeff Braun. This was put together by myself and Jeff Oshinsky from the ESSD National Weather Service in Alaska. Also contributing to this session were Tony Hall, Christine Nelson, and Christina Neal, who also gave us this nice photo background here. Other contributors from CIRA include Louis Grasso and Don Hilger. The objectives with this session take up where the last one left off. We'll be following a little case, the 2009 eruption of Mount Redoubt. We'll follow that up with the organizational structure involved in volcanic ash. We'll be looking at goals surrounding this in the past, present, and future to see how they're going. Then we'll look at the flow of information and see how that relates to actually producing a volcanic ash forecast. We'll move into what volcanic observatories and volcanic ash advisory centers do and their relationship to each other. And then we'll look at the Eyjafjallajökull volcanic eruption in 2010 and look at the great impact that it gave to Europe and really all over the world, and see what kind of lessons we have learned from that. And then we'll finish up with some coming soon future attractions, many of which have to do with the new GOES-R program. First up, a case study with the Mount Redoubt volcano and its eruption in 2009. Mount Redoubt is located here adjacent to the Cook Inlet, and it's only about 100 miles southwest of Anchorage. It is seismically monitored with 10 seismic stations, 1 pressure sensor, and 3 web cameras. It's also monitored by airborne and satellite gas measurements, thermal imaging, 2 real-time global positioning satellites, and several campaign stations for GPS and broadband seismicity. Visual observations are given by aircraft photography as well when it's active. It is important for the National Weather Service to monitor Mount Redoubt because of its recent history of eruptions and also its close proximity to a major metropolitan area such as Anchorage, which has the potential for national impact on nearby oil, energy facilities, and potential serious disruption to air and marine transportation. With regard to Mount Redoubt's history, the last significant eruptions on Mount Redoubt took place from December 14, 1989 to April 21, 1990. These series of eruptions produced a pyroclastic flow that moved down the drift glacier. This resulted in debris flow that entrained ice blocks as large as 10 meters and crested the river about 8 meters above the river channel itself near the Drift River oil terminal, which we'll see in a MODIS image later. These 1989 eruptions were famous also for the Boeing 747 or KLM near miss, which we talked about in the last session, which, if you remember, while en route from Amsterdam, flew into an ash cloud several hours after the eruption and experienced complete engine failure and narrowly avoided tragedy before the crew successfully restarted the engines and landed safely in Anchorage. It was very close. It was a close call. The aircraft actually ended up sustaining $80 million in damages. Overall, there were some 23 major explosive events between December 89 and April 1990. That 1989-1990 eruption readout seriously affected the population, commerce, and oil production throughout the whole Cook Inlet region, and the air traffic was affected as far away as Texas. We couldn't get flights in. Total estimated economic costs were around $160 million, making the 89-90 eruption the second most costly volcanic eruption in U.S. history after Mount St. Helens in 1980. Moving up to the most recent activity in history, which actually began in late July 2008 with unusually strong hydrogen sulfide odors noted near the volcano. These persisted through mid-September 2008. By late September, volcanic tremors began, along with steaming from the top of the volcano, and a 50-meter wide hole was detected in the upper drift glacier. During the month of October, hydrogen sulfide, sulfur dioxide, and carbon dioxide were all measured well above background levels. By October 3, 2008, the Alaskan Volcanic Observatory sent out an information statement describing its unrest and detailed the possible event possibilities. On November 5, 2008, the color code changed from green to yellow and the alert level changed from normal to advisory. The National Weather Service uses the USGS Volcanic Activity Alert Notification System for designations of volcano alert levels, which we'll look closer at later. During the week of January 22, 2009, seismicity dramatically increased and new mudflows began to appear along the margin of the drift glacier at the north base of the volcano. Sulfur dioxide levels were also elevated along with this increase in seismicity. The seismic events going on reflected the magma displacement beneath the volcano and were now occurring every hour at the volcano monitoring stations. By January 23rd, there were slight increases in seismicity at the summit. On the 24th, a 5.73 earthquake occurred about 76 miles south of the volcano, right here in the yellow square area. This is the approximate location of Mount Redoubt itself. And on the 25th, there were nearly continuous tremors near the summit. On Sunday, January 25th, also, the AVO raised the aviation color code to orange in the alert level to watch status, and they began 24/7 staffing. Seismicity began to decline, however, later that afternoon on Sunday, January 25th, but was still above background levels, so the AVO decided to conduct an overflight of the volcano Sunday afternoon. These observations confirmed that no eruption had occurred at the time. However, there was still a good deal of steam and sulfur gas emissions going on. This alert level of orange and watch level remained for about the next month and a half before the AVO decided to drop this alert level back to yellow and advisory status on March 10th, 2009, about 6 weeks after little change in the volcano. Ironically, only a few days after dropping from orange to yellow alert status, the eruption began, which just goes to show how unpredictable volcanoes can be, even when they're being monitored. Beginning on March 15, 2009, at approximately 1 p.m. in the afternoon Alaska Daylight Time, an explosion took place when magma neared the surface. The explosion resulted in a small ash eruption with high levels of gas. A water vapor plume was also observed during an overflight. An orange watch status alert level was then declared. However, 3 days later, it was downgraded to yellow advisory status because of lack of activity, but then again by March 21st, due to a high rate of seismic activity, the AVO returned the orange watch alert level. On March 22, 2009, began a series of eruptions with plume heights observed as high as 60,000 feet during at least 2 of the 6 major eruptions. Ashfall occurred over most of south-central Alaska, including Anchorage, with mounts ranging from a trace to 1/2 inch in depth. The eruptions consisted of a series of explosive ash-producing events that resulted in immediate action on part of the National Weather Service regional headquarters, including Anchorage Weather Forecast Offices, Alaska River Forecast Centers, Alaska Aviation Weather Units, the Volcanic Ash Advisory Centers, and the Anchorage Center for Weather Service Units, the Aviation Unit. The redoubt eruptions disrupted air traffic all over the region, with hundreds of commercial flights canceled, and cargo companies were significantly impacted at this time and could not get cargo into the area. This resulted in employees being placed on unpaid leave during periods when the airport operations were shut down. And now we'll take a quick look at a few of the model forecasts and remote observations for March 23rd eruption. Up first, the puff model. And you notice this is taken a couple hours after the eruption, with the lowest levels of the eruption plume forecast to drift off to the north-northeast from the volcano, which is located here, and the highest elevations of the ash off to the east. And it's all drifting in a general north-northeastward trajectory. Again, Anchorage is down here at the end of the Cook Inlet area. Here's a same look, only using the high split model, trajectory model part of high split. And you notice the same kind of trend here. We have the lowest levels off to the north here, the highest levels off to the east. So the general pattern of the plume at this time would be roughly something like this. So that matches up pretty well. Then we move on to the high split mass dispersion, which is showing us the particle densities in the area. And in this case, we have a rough alignment, the same as similar to what we were seeing in the trajectory and the puff models. However, here we actually see the highest concentrations of particulates off to the north. And again, this is drifting in northward direction. So this might be a little bit more of a dangerous area overall. Then we take a look at the particle cross sections, which match up very well with what we saw in the mass dispersion. As you would expect, the highest particulate concentrations are here off to the north again, right in this red area. Here's a cross-sectional look of what it looks like down here, with the lowest particulate levels at the lowest levels in the atmosphere, and the highest levels somewhere in the mid area here, and then a little bit lower concentrations off to the southeast or east, but at a higher level also. So that matches up very well. Now we'll take a look at what the actual configuration was. This was 2 hours after the initial eruption. You can see how it's drifted away from the redoubt volcano off in a north-northeast direction. And the forecast positions that we saw earlier line up very well with what we're actually seeing in the satellite imagery from the HRR, which is, again, as you know, the Advanced Very High Resolution Radiometer, which shows a false color satellite image of the eruptions. So anyway, everything matching up together. You want to put together the model forecasts, match those up, just like you do with the weather. Find out how well everything is initialized, and then take a look a few hours later, see how well it's doing, so you can adjust your forecast. Here's another look at one of the eruptions from March 23rd. This is taken from the MODIS platform, in this case Terra. It's created at NASA by Jesse Allen. This image was taken about 16 minutes after the third large eruption at 12:30 a.m. Alaska Daylight Time. This one was a little bit earlier than the eruptions we saw in the forecast previously, and we show one plume that has already erupted and drifted off to the north and is continuing in this direction, and a newer plume from a new eruption just occurring now in this round area right here. This is actually the plume that the forecast was made for before, and elongates as it drifts off to the north-northeast over time that we saw in the forecast area. This one right here was taken 4 hours later, It shows the plume is drifted well off to the north-northeast at this time and continues on its way out here, although it's a little bit harder to see. And again, remember, this is infrared imagery. And we've actually got a fourth eruption occurring right now, just starting around the mountain at Mount Redoubt. And if you look very closely right in here, you see a black dot. And that black dot is actually provided from the heat from the volcanic eruption itself. So another use of infrared imagery when the clouds in the atmosphere allow. Here's another look from the MODIS Terra platform a little bit later in the day. This is the visible platform taken later on March 23rd, showing the ash fallout actually over the snow. And again, we do have the advantage of having relatively clear skies and snow on the ground to show where the ash is drifted, which I'm trying to outline here in different areas. And you can see the fingers of ash over this area as the eruption occurred and the drift occurred off to the north-northeast. So another valuable asset, use the high-resolution visible when you can. Here's a good look of a combined image that was actually taken from two separate orbits aboard the Aura from the ozone monitoring instrument on March 23rd and put together to give relative concentrations and drift patterns of sulfur dioxide, which you can see where I'm outlining it here. Red at the time is the highest concentrations of sulfur dioxide, with yellows and blues and purples being a little bit less. But overall, this is a good proxy also for ash locations, which can be used to direct planes around when needed. Next up, we're going to show you how even GOES platforms, this is GOES 11 infrared, can be used for identifying and following trajectories of volcanic eruptions. This is also from March 23rd, just to match up with what all the other images that we've seen so far. This was provided to us from Scott Bachmeyer, one of our partners up at the University of Wisconsin. We'll show you the loop coming up here next. Okay, here's the actual loop of the GOES image taken on March 23rd, and you will notice that the volcanic eruption clouds in this case exhibited brightness temperatures in the minus 50 to 58 degrees, so we're looking at the yellow or yellow to red colors there, and you can see those taken off from about the location of where the volcano is down here to begin with, and we'll kind of follow it up to the north. The first eruption plume goes off well to the north of Anchorage, which is located here. The second one, the elongated one that we saw the model forecast for, you can see how that actually takes the southern end of it right into Anchorage's area. So another very useful thing, especially GOES, because it's time sensitive. It can show the area very well over a long period of time and show the general drift of clouds, even though you're not getting quite as high a resolution of images. Here's a good high-resolution image taken from NASA's Advanced Land Imager on April 4th, 2009, showing some of Mount Redoubt's hazards. Current hazards going on include the volcanic ash plume that you can see here emanating from Mount Redoubt, which is located up in this part of the image. Airborne ash clouds pose a hazard to aviation, resulting in hundreds of cancellations and rerouted flights in and around Anchorage, which is off to the northeast in this particular case in this image. The repercussions of human and cargo transport delays rippled through Anchorage and the U.S. economies as Alaskan Airlines canceled approximately 200 flights. FedEx, UPS, and other cargo airlines rerouted aircraft to Seattle, and ashfall caused the Ted Stevens International Airport in Anchorage to shut down all operations for 20 continuous hours at one time. Disruption to the aviation industry was significant, with long-term and far-reaching economic implications. Also, you notice traveling just off to the north and off to the northeast, down the valleys were these lahars, and two major lahars moved down the Drift River Valley and partially inundated the Chevron oil terminal located right here where it says Drift Oil Terminal. The risk and damage inflicted on the drift terminal cost Chevron oil significantly in these cases. Damage to terminals like these pose risk to surrounding ecological and human communities, and there's also a significant economic impact from halting oil storage at the drift oil terminal, which affects the upstream oil production at the time. And you can also notice the relative location to the adjacent Cook Inlet, which, if the oil gets out into the inlet itself, can destroy the ecology of this water body itself. Here's a quick look at the size of the areas actually affected by volcanic ash advisory, and this is just one of the 11 volcanic ash advisories that were issued between March 22nd, 2009 and April 4th, 2009. Notice the size of this. Here is roughly the location of Mount Redoubt. Here's Anchorage. This was just on one day, and you notice the immense size of the volcanic ash advisory areas that were affected by this, and of course rerouting of all aircraft in and around these areas would have had to have taken place at this time. So you can see the impact to aviation, the economic impact that may occur, and of course if this had been issued to the north and northeast, which several of those 11 volcanic ash advisories were over time, it would severely affect Anchorage itself. And here are a few results from that eruption of Mount Redoubt between March 22nd and April 4th, 2009. Over that time period, there were some 19 explosive events. 16 of the 19 events affected flight levels up to 36,000 feet, and 4 of those eruptions affected flight levels up to 50,000 feet or higher. 2 major lahars moved down the Drift River and partially inundated the Chevron Drift oil terminal, causing ecological as well as economic impacts. Airborne ash clouds caused multiple flight cancellations. Alaska Airlines alone canceled approximately 200 flights over that time period. Ashfall forced Ted Stevens International Airport at one time to close up to 20 consecutive hours. And you have to remember Anchorage is one of the top 5 busiest cargo hubs in the entire world. There was disruption, obviously, to the aviation industry on the whole. It was significant for both passenger and cargo travel and transportation between Asia and North America. Something else to remember is that NOAA's National Weather Service plays a central role in all this in providing the meteorological observations and analysis needed for the forecast and help to issue the advisory information for volcanic eruptions and volcanic ash advisories. As a matter of fact, during the period between March 22nd and April 4th, the Alaska Aviation Weather Unit, which is part of the National Weather Service, evaluated some 142 pilot reports and issued 39 SIGMATs that were all volcanic related. Next up, we're going to go into a little bit of the organizational structure needed to monitor volcanoes and volcanic eruptions. It can get quite complex at times. Just within the National Weather Service alone, we're talking about 2 volcanic ash advisory centers, one in Anchorage, one in Washington, in a joint effort with NESDIS. We also have 3 meteorological watch offices involved. The Alaskan Aviation Weather Unit is one, the Aviation Weather Center is one, and the WFO in Honolulu is one. Then we have all the Regional Center Weather Service Units, or CWSUs, which may be involved when the volcanic ash starts moving and drifting around a volcano. And then, of course, we have well over 100 WFOs that may not be all affected at one time, but nevertheless, the infrastructure involved in getting the communication between the weather offices and all these other offices can also be quite complex at times. Here's a list of the products that the National Weather Service is responsible for and the offices that provide them. Volcanic Ash Advisory Center have to produce the volcanic ash advisories as well as the volcanic ash graphics that go along with them. Meteorological watch offices provide the SIGMATs for volcanic ash. Each WFO that's in an affected area will have to issue volcanic ash statements through an SPS, a volcanic ashfall advisory through an MPW, or a volcanic ashfall warning also through an MPW. Those that are adjacent to large bodies of water that are affected volcanic ash can also expect to issue special marine statements. CWSUs also will have to issue the center weather advisories and the meteorological impact statements surrounding the volcanic ash eruptions. Here's a quick look at the somewhat shortened organizational timeline that NOAA and the National Weather Service have. Also, with a memorandum of agreement with the FAA as well as the USGS from the Department of Interior, back in the 1970s, organized volcano monitoring began. The Volcanic Ash Monitoring Program at the Satellite Analysis Branch became official in 1987. By 1995, the National Weather Service Alaska Aviation Weather Unit, or AWU, formed. In 1997, the ICAO established 9 worldwide volcanic ash advisory centers, one in Anchorage, which is managed by the AWU, and one in Washington, D.C., which is managed through a joint effort between NESDIS and the National Weather Service. In 1998, responsibility for managing the National Weather Service Volcanic Ash Program transferred to the National Weather Service Alaska region, and they provide operational knowledge as well as develop successful coordination with other agencies. As one of the most important parts of the organizational structure, the U.S. volcano observatories give us much information about volcanic eruptions around, especially the United States. This is a subset of the USGS and part of the Department of Interior. There are 5 volcano observatories located in the United States: the Alaskan, Cascades, Long Valley, Yellowstone, and Hawaiian volcano observatories. The research at each of the 5 volcano observatories, in conjunction with the Menlo Science Center in Menlo Park, California, help advance the understanding of active volcanism and allow Volcano Hazards Program to provide warnings of impending eruptions in the United States. They monitor earthquake activity, ground deformation, gas chemistry, and other geophysical and hydrological conditions before, during, and after eruptions. Observations are used to detect activity leading to an eruption, provide real-time emergency information about future and ongoing eruptions, identify hazardous areas around active and potentially active volcanoes, and improve our understanding of how volcanoes erupt and change our environment. For more information on these and the individual volcano observatories, please see the talking points that reference this slide, slide 21. Again, just to reiterate some of the more important points and information that the volcano observatories give us, they understand and give us the eruptive history and style of different kinds of eruptions associated with volcanoes. They systematically monitor dangerous volcanoes around the United States and around the world. They issue warnings and announcements about unrest eruptions and also evaluate false eruption reports, in addition to announcing the cessation or ending of eruptions. And during eruptions, they provide frequent updates on the level of activity involving the hazard itself. They also work closely with the National Weather Service and FAA and other agencies to track the ash clouds and show the other impacts associated with volcanic eruptions. They handle pre-eruption, during the eruption, and post-eruption monitoring, including geodesy, seismology, geochemical, as well as other methods, including acoustic, gravimetric, thermal, electromagnetic, and visual types of sensing. In a joint project between the Alaskan Volcano Observatory and the International Civilian Aviation Organization, or ICAO, they put together an aviation color code for identifying different volcano alert levels. Green, volcano typical background non-eruptive state. Yellow, volcano exhibiting signs of elevated unrest above background levels. Orange, volcano exhibiting heightened and escalating unrest with increased potential of eruption. And red, eruption is imminent with significant emission of volcanic ash into the atmosphere likely, or the eruption is actually underway or suspected with significant emission of volcanic ash into the atmosphere. Here's an example of a product issued by volcano observatories called a Volcanic Activity Notice. It gives a summary of what is going on with the active volcanoes in any specific area and what to expect later on. Here we look at the symbiotic relationship between the National Weather Service offices and the Alaska Volcano Observatories, as well as other volcano observatories. The AVO provides the following support to the Alaska National Weather Service offices. They report volcano history, potential behavior in volcanoes, such as what we saw in the Volcano Activity Notice. provide training on remote sensing for identifying the height of ash plumes in volcanoes. They provide notification of an eruption, including the initial estimate of eruption height and direction that can go into the models. Also, the AVO and the National Weather Service provide mutual support through the Alaska Interagency Working Group for Volcanic Ash, a good communication source. And they act as a liaison to Russia to enhance the communication between Russian volcanologists and National Weather Service offices. Now we'll take just a brief intermission to show you some really great photos. This is a photograph taken by an astronaut aboard the International Space Station June 12, 2009 of Sarychev Peak eruption in the Kuril Islands. This is courtesy NASA Johnson Space Center. The orbit of the International Space Station allowed the astronauts in this particular case to view the Sarychev volcano, which lies just northeast of Japan, early in the eruption stage on June 12, 2009. Sarychev is one of the most active volcanoes in the Kuril Island chain. Ash from the multi-day eruption has been detected as far away as 2,500 kilometers to the southeast and 926 kilometers to the west-northwest of the volcano, disrupting commercial airline flights as well as cargo flights, which had to be diverted away from the region for a period of 3 or 4 days after this eruption. This detailed photograph shows a lot of things here, and we'll be looking at 3 different views, but you can see the intense eruption here causing a very quick updraft, a Peleus cloud here at the top, here in the white where we have the steam and the ash mixed together. The low-level stratus area over here that surrounded the island, which was actually all over the island originally, you can see how the intense updrafts, this like intense convection, went up here, and then we have a downward descending motion around the outside, clearing this area around the outside of the volcano. Another thing we notice here is this area drifting off straight down to the bottom of the photograph here, and that's actually a pyroclastic flow. We can see some other views of something. Here's a close-up view of the Peleus cloud, and over here we have a top view of the Peleus cloud, and then here's the pyroclastic flow. As the space station drifted off around it, they were still taking photographs, and you can see the pyroclastic flow coming down from the slopes of the volcano at that time. Here's just a little more on the symbiotic relationship between the National Weather Service offices and the Alaska Volcano Observatories. The National Weather Service offices in this case provide this information to the AVO. The WFOs and the Alaskan Aviation Weather Units, or AWU, analyze radar returns that they can relate that information on ash plumes that are close enough to the radar back to the volcano observatories, so they can use that for analysis. They also discuss validity of pilot reports. They interpolate webcam pictures and photos that they are privy to. They, during significant eruptions, the AWU, CWSUs, and the AVO hold daily conference calls to discuss the situation, both for the analysis of the volcano and the forecast problems involved. CWSUs also provide customized flight support to the AVO when they do reconnaissance flights. And Alaska National Weather Service offices often initiate calls to the AVO if they get reports of an eruption before they actually hear one from the AVO, or see indications of an eruption through webcams, satellite images, etc. The USGS and the volcano observatories initiated the Volcano Hazards program, whose mission and overall objectives of the program are to advance the scientific understanding of volcanic processes and lessen the harmful impacts of volcanic activity. The Volcano Hazards program monitors active and potentially active volcanoes, assesses their hazards, responds to volcanic crises, and conducts research on how volcanoes work in order to and for the USGS to issue timely warnings of potential volcanic hazards to the responsible emergency management authorities in the area where the population is affected. Thus, in addition to obtaining the best possible scientific information, the program works to effectively communicate its scientific findings to authorities and the public in an appropriate and understandable form. Here are the original goals for the Volcanic Ash program set back in 1995, and all have been reached or are continuing, and that continues to build effective operation-based programs, continuing coordination with other NOAA and National Weather Service offices and associated offices such as the VACS and the CWSUs and the AWU. They coordinate with other national agencies such as the USGS, establish international volcano program and agreements around the world, and continue research and training efforts. Some 9 to 10 years after the original goals were set in 1995, a new set of goals were posted. This includes the 5-minute requirement, which is 5 minutes from detection to first warning, which is a continuing process and sometimes hard. We'll talk a little bit more about that in a minute. To modernize text products to graphics, we now have both in many cases where we have text products and graphics, such as the Volcanic Ash Advisories and the Volcanic Ash graphic itself. This included trying to put weather in the cockpit of the airplanes, which could actually see these graphics. This is an ongoing thing. It's sometimes expensive, so some of the smaller operations don't have this ability yet, but some of the larger airlines and cargo companies do have that ability. To have graphical volcanic ash signets and advisories, I mentioned that just a little bit ago, and to work closely with the international community to ensure these formats work for all and are the same or consistently the same all around the world. Also, to transform current research into operational forecasting tools and techniques. Of course, this is ongoing. We also have a need for the international consistency that I mentioned before, to stay current with research and operational procedures, to break down the language barriers between all 9 VACs around the world so that everybody can communicate on the same level, to offer training, both National Weather Service and external customers, in this particular case, to train them on volcanic ash hazards, which include volcanic ash forecasting, which is still new and ongoing and growing, and part of, we're learning a lot through the weather business itself. Also, operational forecasters must stay current with new monitoring and forecasting techniques as they evolve, and to continually to collaborate with federal, private, and international partners in all these endeavors in order to get something to actually work in the shortest time period possible. So why the need for a 5-minute warning system in this case? In 5 minutes, the ash cloud can be at a flight level reaching above 20,000 feet. In 10 to 15 minutes, it can be 50 to 60,000 feet. Aircraft often approach these clouds at a rate of 5 miles per minute or greater, and often they need that time to divert and avoid the ash cloud if at all possible. So we need to get this out as fast as we can. Everything possible at the moment is being done to implement this goal for every eruption when it is possible, but it is very, very, very difficult to do, and it usually only works in most cases with volcanoes that are actively being monitored. If they're not being monitored by any other sources, it's virtually impossible to do. And now moving up to the most recent goals that we're currently pursuing that are extensions of the 1995 and 2004 goals. These are set to eliminate encounters with ash that could degrade the in-flight safety of air crews and passengers and cause damage itself to the aircraft. That's pretty obvious, but that's one that is always going to be pursued. We want to prevent accidental encounters with hazardous clouds if at all possible. So that may mean monitoring those OMIs and the sulfur dioxide gas emissions a little bit closer and find a good relationship, a solid relationship between those and ash, and see if they actually hold true. Want to reduce the air traffic delays themselves, diversions, or evasive actions that need to be taken when hazardous clouds are present, and present the most efficient and economical way to get around or underneath these kind of clouds. And also, we want to move forward with the development of a single worldwide standard for the exchange of information on airborne hazardous materials, and in this case we're talking about volcanic ash. It's very important when we're moving from one airspace to another to not have any types of confusion. We're going to be talking about the role of volcanic ash advisory centers in just a minute, but I want to tell you a little bit more about the Alaskan Aviation Weather Unit, or AWU, which we've mentioned several times in the past, and what they do exactly. Here's an example of their homepage, front page. Here in yellow we have outlined the SIGMETs and airmets going on at the particular time. They primarily have two roles. One is a meteorological watch office, which are responsible for notifying air traffic control in those areas of in-flight hazardous weather conditions, including volcanic ash. They also act, in this case, as a volcanic ash advisory center. These centers are responsible for providing ash movement and dispersion guidance to meteorological watch offices, which they are one themselves, and to the neighboring VACs so that volcanic ash advisories and graphics can be put out. And now moving on to volcanic ash advisory centers of the world and just what they do. You notice that there's 9 of them around the world, including 2 that cover the United States, one in Washington and the other one in Anchorage. Their primary role, their reason for being, is to develop and execute volcanic ash dispersion models in real time, use satellite information to identify volcanic ash and to discriminate volcanic ash clouds from meteorological clouds, which is very hard to do, issue volcanic ash advisories, volcanic ash graphics, and which each provide guidance to the meteorological watch offices, which we just talked about, for producing SIGMETs involving volcanic ash. They also provide volcanic ash service to regional forecast centers, WFOs, MWOs, and to the adjacent VACs around the world, and also coordinate with the aviation communities extensively and to the public and neighboring VACs about volcanic episodes and what to expect with forecasts or through observations and remote sensing. And here's some typical lines of communication between the VAC and everybody else, including heavy-duty communication between the VAC and the Volcanic Observatory, also with the meteorological watch offices, the adjacent CWSUs, National Weather Service WFOs, the National Weather Service AWC in Kansas City, Air Traffic Control, Federal Aviation Administration, the International Civilian Aviation Organization. All the airlines can contact them. Contact with FEMA, DOD, Department of Homeland Security, and also, accordingly, other adjacent VACs. And then there's the communication between the adjacent VACs and all the rest, and the airlines, and the aviation organization, and the FAA, and the FAA's communication with FEMA, or possibly even the Department of Defense, and of course air traffic control. And then you have the CWSUs contacting the WFOs, which contact the AWC in Kansas City, or the CWSU contacting the AWC directly in Kansas City, on and on and on. So you can see this is a complex line of communication between all these agencies, all ending up here during a volcanic episode in order for them to get out the most recent warnings that they can do. Here's a quick peek just at the Volcanic Ash Advisory Center's homepage, just to kind of give you an idea what's up front here on this particular day. They're talking about Mount Cleveland eruption, or possibility of eruption at that time. It was under a yellow advisory. Here's another schematic that shows the information used, or the input into the VAC for use in generating forecasts and those advisories. We have satellite analysis, which we talked extensively about in session 1. Weather observations themselves, PIREPs from pilots, obviously, ground reports from humans, ground reports from cameras, and radar when it's within range. We also need a lot of information from volcanologists and geologists of the USGS and the volcano observatories that are close by. Get information from television sources and the media. Often they see things right away or are privy to filming them, and they can send that information to the VACs. Also information from the adjacent VACs. If they have information that you haven't received yet, or if you are located downstream from an active volcano, you'll need that information later as the volcanic ash drifts into your area. Also, We all use the internet now, and in some cases where the meteorological offices and the WFOs are not co-located with the VAC, you need to have information from them also to get information into the models. And finally, the models themselves, Numerical Weather Prediction Center, the high split models and the puff models, which we also talked about in the previous session. And now I'll take a quick peek into the volcanic ash forecast process and the actions taken. Much of this information provided by Tony Hall, the meteorologist in charge for the Alaskan Aviation Weather Unit and the Alaska Volcanic Ash Advisory Center. The source of the initial report from the eruption can drive the actions taken by the forecaster. Generally, some quick assessment of the potential threat and validity of the report will drive the first actions taken. In some cases, pilot reports need to be verified, especially for shallow or low-level plumes, which are sometimes incorrectly interpreted, such as leak clouds off a volcano's dome. Other pyreps from the middle and upper levels can usually be taken verbatim and used to immediately contact the CWSU and FAA and issue an eruption SIGMET. The latter example would be the case for domestic volcanoes. The situation gets a little more complicated for Japanese and Russian volcanoes, but for this discussion we'll focus on just Alaskan volcanoes. Again, the first action taken is to call the CWSU and the FAA to allow them as much time as possible to divert the aircraft in a potential risk area away from the volcano itself. This is followed by an eruption SIGMET stating that a specific volcano may have erupted to a reported flight level if known. This SIGMET, and the goal for the SIGMET, is to be issued within 5 minutes of the initial report, if possible, and sometimes that's not possible, but that is the goal, as we stated from the 2004 goals of the Volcano Ash Program. The Volcanic Ash SIGMET is the first product that provides warning for aircraft as well as air traffic surfaces and is essentially a no-fly area for aircraft. However, it is ultimately up to the individual airlines themselves to determine whether they will avoid that airspace or not. SIGMET information is ideal for simple volcanic ash events with uniform distribution of ash. However, larger events that produce large ash clouds moving in different directions at different levels due to the wind shear can pose a significant problem in the production of a SIGMET. The Meteorological Watch Office is the one that is responsible for actually issuing the SIGMET. There are 4 of them, which we mentioned before, 3 of them in the United States, in Anchorage, Kansas City, and Hawaii, Honolulu. However, there is a 4th in Guam. Here's an example, or the example of the first 2 SIGMETs from the Mount Redoubt eruption that took place on March 22nd, March 23rd, 2009. Go over this and just take a peek at it and see what you can glean from it. A wide variety of information or data is gathered and processed in order to produce those volcanic ash SIGMETs and volcanic ash advisories. It's essentially a large fact-finding mission using model data, satellite imagery, and other tools that are available in different platforms, including AWIPS. The forecaster has to make a lot of decisions in a very short period of time based on only the information that he has available at that particular time point. The forecaster in the loop, or the so-called forecaster in the loop, is almost an understatement for this kind of activity. Some of the data that is gathered is PIREP or more PIREP information from CWSUs using the volcanic ash dispersion model. In this case, the high split is the official model used by the VACs. Meteorological model data from other sources in and around the region. Satellite imagery interpretation, including coordination with the AVO themselves and their perspective and expertise on the situation. And any other tools that are available and incorporated within AWIPS, for example, regional and forecast soundings to be used with satellite temperature data in order to determine original plume heights, in addition to plume height information determined from local radars, if any are close enough to the volcano for this purpose. Also, concurrent with the previous coordination actions, both the puff and high split models are run. Those take phone calls, quick phone calls to the Washington VAC. You compare the model output with that seen on the satellite imagery to see how it matches up, just as we do in weather forecasting. And then the next thing is to issue the Volcanic Ash Advisory or the Volcanic Ash Graphics sometime within 20 to 25 minutes following that first 5-minute issued segment, if at all possible. Also, from that point on, we want to continue to monitor and assess the model's output with near real-time observations as necessary and rerun the models as necessary in order to get the best forecast possible. Also, we want to continue to update all those agencies we saw on that call list, communication list earlier. It's a tough job. Here's an actual example of a volcanic ash advisory. This one's for Mount Redoubt on March 23rd, which we talked about at the beginning of this session, giving information on the warning conditions, red in this case, location Mount Redoubt, observational data, as well as forecast information for forecasting where that volcanic ash is going to move. This is the companion piece to it, the volcanic ash graphic that goes along with the text, showing graphically where the ash is going to move over a period of time. This is the beginning, this is next, ash plume gets a little bit bigger, and then by the end of the ash advisory, the 18 to 24-hour period, showing the aerial extent of the ash, or where it's expected to be anyway. Anywhere from 3,000 to 6,000 volcanic ash advisories are issued from the 9 VACs around the world every year, with 800 to 3,000 associated also with volcanic ash graphics. Typically, the Washington, Darwin, Anchorage, and Tokyo VACs are the busiest and account for roughly 80% of the annual total of these volcanic ash advisories. This is primarily due to their proximity to the most active volcano alleys, such as the Ring of Fire. And now we're going to switch gears a little bit and talk a little bit about a recent event that had wide economic repercussions, and that was the eruption of the Eyjafjallajökull volcano in Iceland. Air transport industry is very significant and accounts for just under 1% of the world gross domestic product itself and 35% of the world trade by value. The total loss of aviation to the 2010 eruption of the Iceland volcano is estimated at $2.3 billion, with another $2 to $3 billion in losses to the tourist service industry. This brings a total of about $5 billion in total loss. This event brought out just how clear and how important air transport is to the modern economy. Here's a loop of the Iceland volcano, the Eyjafjallajökull volcano erupting at one point. You can see the volcanic ash plume taking off and moving generally upwards, not real high, but sort of being carried off with the winds slowly to upper levels, but the intense fallout below that ash cloud over a rather short distance where you would not want to have any type of aviation or really any kind of transportation units moving into an area like this at this time. But depending on the wind flow at upper levels, just think of the far-reaching applications or repercussions in this case. Here's a quick look at the statistics, the graphics on the impact of the European air traffic for the week of April 15th through the 21st. Here in purple, we have the normal air traffic numbers on each one of those days, and then in gold here are the actual numbers during that week, and you can see how they fell drastically. 54% of the flights didn't operate at all. 100,000 flights were canceled, and that represented 1% of the entire annual traffic. Here's a little bit better way to look at it. This is before, roughly where the numbers stand. This is during that week, and you can see the big dips, and then after, of course, after it recovered a little bit. Still down a little bit for a while after that. But you can see the direct impact on air traffic, which is a direct impact on the economy. Here's another graphical look on the impact to air traffic during that week. This is an image taken from the normal air traffic the morning of April 14th at 1500. You can see a lot of heavy traffic through the entire European region in all directions, nothing being stopped really. The volcano is just starting to erupt, and it's only affecting a very small area at that time. However, 4 days later, you can see how everything has been cut, traffic has been cut, everything's been diverted well south through Spain and southern Europe into Asia, and there's a huge area that's essentially a no-fly zone at this time south of Iceland. Here's an animation made by the Norwegian Meteorological Institute that shows the accumulated ash over a 5-day period between April 15th and April 19th. The yellow indicates ash that has fallen by itself. Red ash has fallen as a result of precipitation, and black is where the ash clouds were at that particular moment in time. But the idea here is to see the large, super large area that's affected by all this. Even parts of North America over here well to the west are affected with this. So it's not just the downstream people that have to worry about this, or the people in the immediate area of Iceland either. Here's a look at the tools used to monitor the Parícutin volcano and the ash plume that resulted from the eruption over that period of time. Operational satellites, aircraft, and the resulting PIREP reports, weather radar, web cameras, lightning detection, and even geodetic measurements. We'll look a little bit closer at some examples coming up. The Iceland volcano was covered by many satellites of various types, including geostationary such as the Meteosat satellites, which we saw examples of in the first session that we took, and also the MODIS platforms. This is MODIS Terra, actually taken from one of the late eruptions on May 7th, 2010. And it's always nice to see these because they're nice high resolution, and you can easily see the drift of the plume off to the east-southeast from the island. And very close, you see a heavy ashfall area out here, or what appears to be ashfall, but it actually turns out to be something else, and we'll look at that in just a second. This is the same image, just a little bit closer up, showing the drift off to the southeast that we were talking about, and that low-level plume in close to the island. This is actually a stereographic view. The multi-angle imaging spectroradiometer aboard the Terra satellite has 9 different camera angles, and each view the scene from a little different angle nearly simultaneously. And by combining all these images using a hyperstereo technique, we can calculate the height of the ash plume. Most of the plume resides between 4 and 6 kilometers, 2.5 to 4 miles above the ocean surface, and is represented in the orange and red color. However, the ash descends to nearly 3 kilometers or 2 miles far downwind in the yellow-green area, which is down here a lot further to the southeast. Also, the smaller patch of ash that's within about a kilometer of the surface, this blue area down here, which we saw over here, which looked like extreme ash fallout, turned out to be ash that was actually resuspended by strong low-level winds. So this is another handy feature that we can go at, and in particular with the maritime traffic in this area, we want to keep the boats and ships out of this area at this time, and of course any low-level flying aircraft. Even though this isn't a direct result of the eruption of the volcano at that time, again, it is resuspended material that's actually being picked up on the satellite. There's nothing quite like having good aircraft observations during these time periods, although it can be rather hazardous for the aircraft themselves. But aircraft observations give great physical and personal perspective to any volcanic eruption. The ash is dispersed in layers often, and the dispersion is dependent often on the local weather. And of course here we have the main eruption from the volcano going up. We have 2 inversion levels above that, one being drifted off rather close to the volcano, another one where it punches through, it actually gets up to a higher level before drifting off in this particular situation. Also, we see good indications through this photograph from the aircraft of heavy volcanic ash fallout in and near the volcano itself. Very important. And just as important are the PIREPs that go along with these kind of things. PIREP is a report of the actual conditions encountered by the aircraft in flight, and pilot reports are critical for air safety, especially during volcanic eruptions. Conditions change quickly, and there's nothing like having a good PIREP to give you a bird's eye view of what it's really like up there. PIREPs can also be used to validate forecast conditions and how models are initializing, especially the dispersion models. The main thing to get from this too, or another thing to get from this, is that forecasts are improved as the result of PIREPs being made to the forecasters that they can actually put into the dispersion models to help them get an idea of what's going on better and what will happen in the future. Radar can be great to monitor volcanic ash eruptions if it's close enough to the volcano. The main observation method to monitor the plume height in this case was a C-band weather radar that was stationed in Keflavik Airport about 160 kilometers away. This made it a little bit difficult to monitor the plume height below 3 kilometers because of the curvature of the Earth and the surrounding landscape. Also, at that distance, the resolution of the radar was about 1 kilometer. The radar did not work well in cloudy conditions, as the ash plume is a bit less reflective than water vapor and disappears in the cloud. Dry ash can also be difficult to monitor due to the low reflectivity and the long distance from the site. The radar worked well during the eruption to monitor the height, or the initial height, but proved to be of little value to monitor the production change parameters as the ash drifted down, and also when you had ash versus water vapor content in and around the plume. We all know that webcams have infiltrated almost all parts of our lives, and it's no less true with volcanic eruptions. Here we have a good example of some webcams put up by local telecom companies that were put up to monitor the eruption. The cameras proved to be very helpful in monitoring changes in the ash content of the plume and gave a good visual feeling of the intensity of the eruption at certain times. Here on the left we have a visible image during the day. Here on the right we actually have an infrared image of the same area, and you can kind of match up places that are the same over here where we have the colder snowfield showing up well in the visible here, and at night it shows up in this area, this little bit darker area over here on the left. But very good for monitoring the volcano 24/7. Another tool that's used routinely to interrogate weather and severe weather situations, lightning detection. Yeah, lightning detection even with volcanoes, and it proved to be a good estimate of high production rates of ash within the plume itself. Electrostatic activity increases with increased ash production. This was used as one parameter to estimate the production rate, which was also put into the dispersion models at the time. Here's a little bit of a look of the actual lightning detection parameters, the number of lightning hits. This is the early eruption in the middle of April. Another one you can see later in April on the 29th, and then the other large eruptions that occurred during the middle of May. But you can easily pick up from this when the activity from the volcano is most intense, especially with regard to volcanic ash. Of course, physical measurement and monitoring of any volcano is particularly important before, if possible, but especially during the eruption itself. Measurements of height, temperature, gravitational field, and chemistry, all in the three-dimensional time-varying space at the environment around the volcano, are made routinely if possible, and along with the seismic instrumentation are used to help forecast future activity of the volcano. It's interesting what a rather typical or even small volcanic eruption can have, but due to its timing and location, it can mean a great deal even on a worldwide basis. And because of that, 3 conferences were put together rather quickly to talk about all this, one in Montreal, Canada in July, and 2 in September, one in Keflavik, Iceland, and the other one in Anchorage, Alaska. Some of the conclusions from this included the weakness of the overall forecast at times, and it was limited mainly because the data available for monitoring the actual ash output at and near the source was not very good. Therefore, a lot of the forecasts were based on proxy estimates of the actual ash discharge instead of the actual ash discharge itself. As a matter of fact, it was found that the predicted ash concentrations were consistently significantly overestimated, which is not good when it's those kind of things that are driving, especially in this case, air traffic in certain areas, and it's completely shutting down economies because of that. The overall conclusion was that there was a need for a strong, successful way to integrate satellite, airborne, and ground data all together and get the best real data that they can in order to put that into the forecast and modeling processes to be able to better predict aerial coverage, both vertically and horizontally. And at times, the models got the horizontal predictions fairly right, but the vertical displacement was often way off, and they could have used this to their advantage by being able to fly either over or under some of these ash plumes, but instead the whole airspace was effectively cut off. From a technical standpoint, there's a great need to improve the availability of accurate information concerning ash concentrations, which we alluded to previously. Inspection of engines that were exposed to forecast volcanic ash resulted in this case in nil findings. So there was disagreement, because right now we've been talking about, or they have been talking about, a concentration of 2 milligrams per cubic meter as being the level with which you cannot fly through, which will have damage to an engine. But Rolls-Royce determined by investigating some 350 engines at the time that this level, this concentration, did not cause damage and was not unsafe. So then the question arises, just what is a critical concentration, or even more importantly, what is the time needed, the critical accumulation of ash through time? Because obviously if you're flying through 2 milligrams per cubic meter for 15 seconds, that's a lot different than flying along an ash plume that has 2 milligrams per cubic meter or greater for 15 minutes or a half an hour or an hour. So there's a lot of research that needs to be done in this area. In the meantime, manufacturers and airlines still advise that the operation of aircraft in these areas, especially where ash is visible or discernible by any means, to be avoided at all costs. But we need to find a better way to get around that in order to economically and efficiently operate during times of volcanic eruptions. Some lessons learned. We need to further review vertical segmentation of the forecast products in order to maximize the use of non-contaminated airspace, and we alluded to that just previously too. Yes, you can fly around it, maybe to the left, to the right, to the west, to the east, but we also need to get a good idea of what's going on in the vertical and where those levels are and where it's safe to fly, whether it's under it, over it, somewhere through the middle. But we need to be able to see that observationally and model that also. Need to obviously further refine the safe levels of ash concentrations, and this is one of the big question mark areas that's going to have to be answered over the next few years. And as proxy measurements, and we talked about this in the first session, we use the OMI and sulfur dioxide levels in the atmosphere to often proxy the locations for volcanic ash. But the question remains, is it really a good proxy, or is it just the best we have? But we need to find a way to actually get a better handle on this and know that, if we're seeing gas levels, are we really also seeing volcanic ash at some levels or at dangerous levels? We need to also consider longer duration volcanic ash training exercises in order to increase participation and increase awareness, and to be able to improve the coordinated response to future volcanic ash events, especially in populated areas. Very important here. Overall conclusions from all this and all the debate and all the discussions was one thing that everybody did come together on was that there was a strong need for thoroughly reviewing and improving all aspects, and of course this means a lot of work, of this complex system. Whether you're talking about just the volcanic eruption itself, how to monitor this in real time during the eruption, before the eruption if possible, and then how to put all this in the numerical models to give us a better idea what's going on, where it's going on, and how to avoid the disastrous part of it all. We need to get to that to be able to efficiently and deliberately respond to this enormous impact of volcanic eruptions, which we saw in dollars and cents. I mean, with this Iceland volcanic eruption in April and May of 2010. And now we're going to look into the crystal ball and look into the future to see what's on the horizon as far as volcanoes and volcanic ash. Coming quickly in the near future to a WFO near you is the Interactive Collaboration in 4 Dimensions, or IC4D. It's a new tool for producing 4-dimensional aviation forecasts, which will obviously have greater repercussions for aviation forecasting than just volcanic ash, but all meteorological parameters. IC4D will allow for the creation of aviation forecasts and a fully gridded forecast that are kind of analogous to what the GFE does right now and what we've been using with that for nearly the past 10 years. IC4D will generate aviation forecasts across the full volume of airspace from the surface to jet level altitudes and at the time intervals needed. It is fully four-dimensional, 3 in space plus time, and allows manipulation of all these fields in 4 dimensions in a meteorologically consistent manner, which also includes volcanic ash modeling and production. Here's a look at how it will look, a nice high-resolution display. IC4D is not your basic GFE, but a modified version of it, a 4-dimensional editable parameter version. It's based more on providing the forecaster improved guidance instead of just model-generated forecasts. It's more forecaster-driven, forecaster-based than product-driven in this case. It's used to produce high-resolution digital aviation forecasts. IC4D, why? To move deeper into the modern digital database world, including verification and activities, and we all know how important verification can be at times, whether we're talking about forecasts or models themselves. It brings the Alaska Aviation Weather Unit into the gridded forecast concept, which the rest of the WFOs have been doing for nearly 10 years. And for aviation, current WFO graphics do not fully address aviation needs, and that's always been a little bit of a weakness. Here, users are requiring better graphical products, and they're going to get it in IC4D. Volcanic ash advisory graphics can now be produced from either the high split model, which can be put into IC4D, or the puff model. And also, output types will be compatible with multiple user systems all around and be transferable over to, say, AWIFs. The grids will also produce turbulence and icing information for aviation, upper-level winds, which can be important for volcanic ash forecasts, freezing levels, convection, which is always important, and, in our case, volcanic ash and visibility restrictions. That's what we're talking about here. Also, cloud cover, pressure coordination with the adjacent WFOs, and numerous other guidance grids. But it's the visual look at this thing, the database that it's using, and the amount of information that can be put into it, and the fact that it is forecaster adjustable or very easily adjustable that gives it great latitude. Here's another way it looks. In this particular case, the initial puff model output is ash concentration in this situation. Values at the grid point locations were for every 500 meters. The ingest process that stored the puff model in this particular run was put into a puff database within the IC4D itself, so puff can be launched within the IC4D, and performs a vertical averaging in order to produce average ash concentration in 3 distinct layers. And we're talking vertically here, which is important. Low from 0 to 5,000 meters, mid from 5,500 meters to 10,000 meters, and high above 10,500 meters and on up. So this might be able to give us a very good visual representation of what's going on, not only in the horizontal but also in the vertical. And now we come into the realm of synthetic imagery or synthetic forecast imagery, which was born out of the GOES-R program, which will become operational near the end of the decade. Here on the left, we actually have a synthetic image generated from cloud models within the WRF model platform. Here on the right is the matching real-time image from GOES 13, and you can see great similarity between the two. The idea here was to be able to actually model cloud fields through and give you an idea what it would look like on the satellite platform through using model forecasts themselves. This is quite unique and looks very different from what we see now. Here's some of the motivations and goals, but down here one of the main goals was to aid in the development of algorithms aimed at aerosol retrievals, which included smoke and ash, and of course ash from volcanic eruptions. So what are we going to get with the new platform, new GOES-R platform? Well, currently we have 5 bands to work with. The visible is approximately 1 kilometer in resolution. We get about 4 images per hour. Routinely, we can get more than that if we call RSO. And we don't have any visible reflective bands as on-orbit calibration. But with the new GOES-R platform going up later in this decade, we're going to have 16 bands to work with. Our visible resolution is going to be 0.5 kilometer. Infrared is going to be 1 kilometer, which is what the visible is right now, which is pretty darn good. We'll have 4 full disk images 4 times per hour, and routinely we're going to increase that to 12 per hour, so that's every 5 minutes. So that's what we get with RSO right now, but that'll be our routine numbers. And on a mesoscale level or scientific level, we can get images every 30 seconds if needed. How is synthetic imagery created? Well, first we input numerical cloud models such as RAMs, WRF, or COAMPS. We can use the microphysics from these. And then we run the cloud model and use the output as input to generate the synthetic GOES 11, GOES 12, or GOES-R in this particular situation, satellite observations that we would see at different channels. This product is a combined effort between the National Severe Storms Laboratory in Norman and CIRA, Cooperative Institute for Research in the Atmosphere here in Fort Collins. Daily output from NSSL's 4-kilometer WRF ARW model is provided to CIRA, who then generates the synthetic satellite imagery, which is then sent back to the Storm Prediction Center for their use. Every day at 0Z, NSL runs the 4-kilometer WRF. As soon as the 12-hour forecast is completed, several variables are extracted and sent off to CIRA. These variables include temperature, water vapor, and other physical and microphysical parameters which are needed for the next step. When all the variables have been received at CIRA, an observational operator is then run to generate synthetic imagery for GOES-R ABI bands, and there are 4 of them that we use right now, and this is if we're generating the synthetic GOES-R imagery. The simulated imagery is then converted to Mercatus area format files and made available back to SPC, who then makes the output viewable on AWIPS. Hourly output between 12Z and for the next 36 hours is processed and available for SPC to use. This product has 2 primary purposes: to generate synthetic imagery from cloud model output that can be used to evaluate each model run. For example, one might compare a simulated water vapor band to observe GOES imagery from, say, between 12 and 18Z, and you match those up with what you're actually seeing in the 12 to 18Z time period and see how well they match up, and that gives you a good idea how well the model initialized. And 2, since the simulated bands will be used on GOES-R ABI, and this is what we'll be looking at in the future, it's good training for getting an idea of what we'll be able to see at that time, and good research and for now to find out what we can do with all these extra channels that we're being given. Here's a quick look at 12 of the 16 bands that we'll be privy to on the GOES-R platform when it comes. This was actually run for an earlier period back on May 8, 2003, a severe weather day in Kansas and Missouri, just to give you some kind of an idea of the different look at the different bands. And remember, too, not only do we have just the bands themselves to look at, which we can see a lot of them look very similar to each other, but we will also have the ability to difference or combine a lot of these together in different ways to come up with different looks, and some of those have yet to be determined. Here's a look at the real versus synthetic side-by-side comparison of the GOES 13 imagery for April 24th, 2010, a slightly severe weather day, and the WRF ARW forecast parameters using GOES-R synthetic imagery here on the left. In this case, the model does a fairly good job with the timing of the convection forming in the southeastern part of the United States, but appears to overdo the coverage some. The brightness temperatures in the clear areas match well, but the model has a cold bias within the thin cirrus cloud areas over the Great Lakes region. So these are a few of the differences that we need to look at over time, but overall it gives us a good indication of how well the model is doing. And now here's another type of synthetic imagery that's a little bit of an offshoot of what we've seen before. This was taken from October 23rd, 2007 with a real-time image over here on the left provided from MODIS. We can easily see the smoke plumes drifting offshore and off to the west of California. Here on the right, however, is the synthetic images that were generated through the model by just giving them the locations of the fire to begin with, and you can see that it did the rest. And this is what we'll be able to see nearly through the entire daytime period, which we can't do right now. Smoke detection with GOES-R using the ABI will exceed current GOES capabilities, as thin smoke plumes are only visible during low sun angle periods, while the GOES-R platform will be able to highlight these areas during the entire daylight period. And this is because of the inclusion of the blue band, or the 0.47 micron band. So this is why we've been talking about this synthetic imagery as of late. You've probably been scratching your head and asking why we're covering this. Well, here it is. And this is just the beginning, and a lot of work still needs to be done. But we went one step beyond the synthetic imagery of generating the meteorological parameters and the smoke production to see if we could actually generate a volcanic ash plume, which we can see here. It's represented in this area right here if you're having a hard time seeing it. But this is from a hypothetical eruption from Yellowstone, Montana, or Yellowstone, Wyoming, if we had one. We placed it during the meteorological conditions on June 28, 2010 last year to see if, using the optical properties given to us for volcanic ash, if we could actually visualize these and produce these. Now you see the clouds themselves from the thunderstorm production stuff look a little bit cartoonish, and that's going to be something that needs to be dealt with. But overall, I mean, we're seeing a pretty decent representation of what we would see in the visible wavelengths here for not only meteorologically produced thunderstorms, but also an actual volcanic ash plume. So this is something to look forward to in the future, and hopefully we'll be able to take this information, mix it with the information that we get from the high split and puff models, the dispersion models, and actually be able to produce forecast volcanic ash plumes and get good forecast data from that we can use. Well, that's it. That's the end of the second part and the end of the two-part series of Volcanoes and Volcanic Ash. For more information concerning this session and others, please see the student guide and the talking points, and we also have links on those sites to many other good links that you may want to look into for further information. As far as personal contacts go, you can contact me here, Braun@cura.coloradostate.edu, if you have further questions and or comments. Thank you.